All right, it's going to be slowly the time to restart. Pavel, I see that you are unmuted. I mean, it's no problem, just to let you know. We are back close to 50 here online. We are, again, 10 in the room here. We're going to slowly restart. The idea of this early afternoon will be to actually start with a point about Sophia. You should see the slides moving. Don't forget about the vote, right? You're 50 online. We still have like only, I think, 20 or a bit more votes. So do not hesitate to vote for the best open source, according to you, contribution. And so, yeah, it's exactly 1:15. Let's restart. So I'm going to make a few updates about the community of SOFA and the worldwide community, and then a few words also about the SOFA awards, the different actually applications that have been done and the different candidates. So yeah, we're going to look at the updates of SOFA, updates about the community, the consortium, a point which is quite important for not only SOFA and the consortium, but actually for the entire community, its recruitment, and how to get involved. So a few updates, and I thank Erik and Infinitec for the image of the slide. So the updates about SOFA, there have been actually many fixes and clean on especially the topological changes recently, new features on solvers. So for that, always do not hesitate to get back to the changelog of SOFA or to the page on the SOFA website. You should see my screen, yes, on the latest release that will give you all the latest updates in SOFA, so in About and SOFA v22.06. A new page should soon appear for the new release 22.12. In plugins, there have been many things also ongoing, and you heard and you'll keep hearing about them today. This in the next session we're going to have both actually Erik talking about the different projects maybe involving topological changes, but also Robin, who will speak about DeepPhysX, which is the platform coupling SOFA and possibly PyTorch, but on the framework as well for making AI application coupling simulation and AI. Other plugins again on linear solvers, as I already mentioned in the first bullet points, and many projects are ongoing. If your project is not on the list, if you'd like to give a highlight sometime on your project, never hesitate to solicitate us for promoting it. And if you are writing a proposal, we can also definitely help for adding some open source keywords and stuff like that in your proposal. So never hesitate to contact us. For all the updates, technical updates, there will be more on the technical committee starting tomorrow, so do not hesitate to join us as well. All the links has been sent theoretically after your registration or at the latest last week. About working with SOFA, just know that whether you are in Indonesia or in France or in Cambodia or whatever, Mexico or any other country, basically you can always get support from the community. Whether you're struggling installing SOFA, you can always go on the GitHub discussion forum. So it's everything on the GitHub account of SOFA. If you are struggling with the API and developing in C++, you can also go there on the GitHub discussion. Or if you want to chat with the devs, you can get them directly on the Gitter chat. So that it's really an open chat. All you need for both the forum discussion and Gitter chat is a GitHub account, nothing more. And if you notice a bug, improve the code in SOFA, please, either open an issue, open a pull request, just let us know, and we'll guide you through the process of pull request, the peer review process, and so on and so forth. You have all the information on the Get Involved page of the SOFA Frameworks website. Here, community, get involved, how to cite SOFA, how to contribute, how to report a bug, and so on and so forth. If you think we can improve things in a way or in another, please let us know. A few digits about the activity. You see the number of pull requests. About between two releases, there is about 350 pull requests, meaning that there is actually way more commits and way more changes than that, because a pull request is a set of changes. about 500 downloads of the binary only per month, unique cloners, so from the sources to more than 200, and quite a nice activity on GitHub discussions as well. I'd like to thank all the developers who are actually active, and also the users who actually dare and are actually not that shy to actually post their questions. So please use the forum as much as you want. For 10 years now, SOFA counts 7 startups that have been created and a company using SOFA. If you are having your own project, if your startup is starting with SOFA as well, or needs some stuff with SOFA, do not hesitate neither to contact us. So yeah, the idea of really sharing your news, all the SOFA social media belongs to you as well. So if you need to highlight something, whether you are a PhD student alone using SOFA in your lab, or whether you're a big lab or company using SOFA, never hesitate to get in touch. That's the mission of the consortium. So just as a reminder, the SOFA consortium aims at really fostering contribution, helping you using SOFA, taking care of the maintenance of SOFA, and coordinating the developments. That's for actually the members and the partners which are financially supporting SOFA. That's one of the most important way to really support SOFA, either being like one of the member, technical or strategic, or donating money as well. That's another way. But this is definitely not the only way. We'll see that. But for us, that matters. Like if your lab or your company is using SOFA for some time and you are and your colleagues are actually happy with it, please make it official. It will definitely help us get more. It won't help us getting rich, but it will help us getting more engineers. Definitely more engineers. So this is something which is really important for the project. So let's make it official if you can. But money is not about all, especially for open source project, even if it's important, obviously. But consortium members and donations brought us like fundings, money, but you can also really support the project by simply contributing a patch, a new feature, a new model, a new algorithm, using and citing SOFA as well. And I'd like to thank as well all the institutions which are actually letting their engineers and researchers use, develop, and take time to work with SOFA. So that's something which is very important to us. If your institution is missing here, let me know. I would be just happy to really add as many logo here as possible. It's just important for us that your institution is indeed represented there. So yeah. I was saying that I was going to talk a bit about recruitments. The whole community really currently is recruiting. The whole community is recruiting, whether at the SOFA consortium, that's actually the image on the right-hand side. We are looking for DevOps, senior engineering developers, sorry. And there is also like research teams that are looking for profiles, companies that are looking for profiles as well. It can be, so for research PhDs, can be postdoc, it can be engineers, and for companies, obviously most, I would say, rather engineering profiles. But if you are interested, in finding a new position, please do contact us. You have the email here at the bottom of the image, or contact us directly through the forums or through the chats that I mentioned before. We have also a LinkedIn page where we try to actually propagate all the information and forward all the information about jobs, but not only. So never hesitate to follow us on Twitter, LinkedIn, YouTube, whatever. It's actually quite cool to just get the information forwarded efficiently. So I'll say that one more time. If you are looking for a position, definitely there might be something suiting for your profile within the SOFA community. So that's the last message before presenting you the contributions of this SOFA 2022 edition of the SOFA Awards. That's how to be active. I mentioned already, like financially supporting the project, obviously through donations and memberships, but you can really be active in your any own way, whether it's actually contributions, helping people on the forum discussion, helping us improving the doc. It's like a huge amount of work, and that's definitely something that could be shared, or at least that you can make feedback that some pages are actually missing. So yeah, and talking about so far all the possible media, obviously, but really try to take your part here. It will definitely help us to increase the development forces, basically the engineering forces around the open source project. Now, before going to the first session of the afternoon, that will be about numerical methods and artificial intelligence, AI, I'm going to present you very briefly the 6 award candidates that applied for the awards competition. And just as a reminder, there is always 2 prizes, one which is actually given by like a jury, which is electing before the SOFA week, electing the best contribution according to several criteria. So thanks a lot to Paul, Camille, Damien, and Eleonora for taking the time to evaluate, make feedback, and yeah, taking really the time to technically evaluate each of the contributions. That were actually the criteria that were used, like technology readiness level, potential impact, documentation, if it's easy to install and use, complexity of the contribution. And since we really want to promote external contribution, there were actually something additional for help, promoting and putting forward the people that were external contributors. And today, and that's the link I'm sharing with you since this morning in the chat, and I will continue to spam you in the chat with this link. You can, as the public of the symposium, you can definitely vote for the public prize, electing according to you what would be the best contribution among the 6 awards. And I'll start right away. So with Paul, who presented Memento Memory, there will be Vladimir on SOFA cutting. There is a Stefan on linear solver on GPU, Alex on JSON reader, Erik on a Turing plugin, and finally Fabrice on a four-wheel Summit XL Twin. So I think for a matter of time, Paul, are you available already, or?
Yeah, sure.
Cool. I can pass the slides if it's fine for you, so that
Sure.
that there is no time. Okay, cool.
So yeah, hi. My name is Paul Maria Scheikl. I'm a PhD student at KIT in Karlsruhe. And I kind of went over SOFA and found some memory leaks that occurred when I was kind of weirded out by, okay, why does SOFA crash all the time if I run reinforcement learning for a long time on environments with a lot of resetting? And a lot of them are just, yeah, program flow memory leaks where we save a state but don't restore it. We collect objects for caching, or just regular memory leaks, also some weird OpenGL stuff. And on the next slide, I kind of summarized my workflow for finding them. So first of all, you've kind of think, okay, why is SOFA crashing? Might be a memory leak. And we can use memory profilers from Python, for example, to just look, okay, what happens when does my memory increase? So that's on the right part of that slide. And after that, I kind of remove all of the objects until the memory leak disappears to kind of identify what might be the object that creates this memory leak. And then there's a very, very nice option that you can pass to the compiler, which is an address sanitizer that compiles the whole memory profiling into the binary of SOFA itself, so you don't need a valgrind, for example, anymore. That then outputs something like that on the left corner of the slide. So you see here, okay, it tells you, hey, there is a new that leaks this and that many bytes and so many objects. So it's much easier to use than scrolling through pages and pages of valgrind output. And then on the next slide, I do believe are some of the pull requests that were created from that. I don't think it makes sense for me to individually go over them, but yeah, a lot of them can be solved by replacing a lot of created raw pointers. So when you say new and then an object class with reference counted pointers such as make shared. So as soon as you don't have a reference anymore on that, the object gets cleaned up correctly. And on the next slide, I think it's just a continuation of that and the current open one that is kind of showing the limit of what that can do. So right now, if you reset an environment, a whole frame buffer copy of the environment leaks. As you can see here, there is 60 megabytes leaked, but it points to an malloc of STL, so deep in graphics, so you can't really pinpoint down where this object gets leaked from. So if you have any ideas, please contact me. I think it's an open issue on the GitHub pages. Cool, thank you.
Thanks a lot, Paul. I'm going to switch to. Sorry, that was the summary of the contribution. Sorry for that. All right. So yeah, there have been actually many pull requests. If you want to contact Paul, that's all the information. But you're going to hear about Paul in the next session. There is, and it has been presented earlier, but by Vladimir, there is another application which is the plugin for interactive cutting, coupling SOFA and Philosophia, which is using filament for rendering, which has been presented earlier by Vladimir, which is another contribution of the year. The application of Alex, who contributed a JSON reader to actually add the feature in SOFA to read scenes which are not written anymore only in XML or in Python, but also using JSON. Let me know if there is anything which I miss, Alex. A tiering plugin from Infinitec 3D from Erik Pernod that is being developed for implementing actually tiering in SOFA, which is all what I'm mentioning here. Since it's the SOFA Awards, we are talking about open contributions. Therefore, all those plugins are actually open source. You can check them out, test them, and definitely, as I said earlier, vote for your preferred actually contribution. And that's the model used for in the tiering plugin. And last but not least, am I missing one here? I don't think so. Yeah. And last but not least, Fabrice, who is a young actually engineer working around SOFA in robotics, who developed a plugin. Actually, it's a Python plugin which allows to model, simulate a Summit XL robot in SOFA. It's this four-wheel robotic platform here developed by Robotnik. And if I can go to the next slide myself. Okay, sorry. And it implements, so first, the control of this robot, the contact modeling of the wheels against the floor. It allows to actually control this robot through ROS2. And all this is written using Python and especially using the prefab principle, which makes that easy actually to reintegrate into new other Python simulation. That was the comparison regarding the accuracy of the simulation of the robot. Here you've got that regarding different speeds. So that's a short video that you can see here of the robot being controlled. And as mentioned before, since it's using the prefab, you can actually add any kind of other tool to the robot, like here a trunk on the top of the robot. You could actually add anything you like for your own robotics purposes. So all those contributions can be found, actually, I can show that to you here on the SOFA Week 2022 webpage here, SOFA Awards widget, and you have the list of the different candidates, sorry. And I'll send you the link again so that you have all the information to vote for one among the 6-year contributions candidates, the one you actually prefer at the following address of aframework.org, SW22 vote. For this afternoon, we are already like 3 minutes late. I'm gonna call Erik on stage for presenting the updates, activity updates from Infinitec 3D. I guess it's gonna be like dense as every year. You should be able to either connect, or if you're already on WebEx, you can share your screen as you prefer. WebEx will be, I think, easier for sharing. And I'm gonna restart the timer. Yeah, we're gonna start with a 5 minutes delay. It's not a big deal. And I will say that again for anyone in the audience, please prepare your question, and if you have any question, do not hesitate to, at the end of the presentation, unmute and ask it or post it into the chat. I would ask it for you, but don't be shy. All right, so it's my pleasure to hear about the update activity highlight from Infinitec 3D. You should be able to share your screen. Great. Perfect. We can see it. Yeah.
Yes. Okay, thank you, Hugo. So I'm going to speak about recent activity in Infinitec 3D in 2022, linked to SOFA. So for people who don't know what is Infinitec 3D, the idea is it is a company to support the open source framework of SOFA by actively contributing to the open source code, also to the different open source plugins, but as well on private plugins. And the main goal is to integrate and evaluate all those code inside, all those features inside Unity. And at the same time, the idea is to provide some consulting and tailored development on either the open source version of SOFA or private plugins, and to integrate them inside Unity. And this allows us to continue contributing to the open source framework of SOFA. So very quickly, I will just say that how does it work to integrate SOFA inside Unity? So inside you have to load an asset, specific asset, and you can load what we call a SOFA context inside Unity. It creates like an interface where you are able to change the different parameters from SOFA, so like gravity, time stepping, etc. You are able to load simulation scene either in XML or in Python, and define also the plugins you want to use. And once you have loaded the simulation, your scene, you can see it inside the Unity editor. You have access to all the scene graph and the different components. And you can interact with those components and run the simulation inside the Unity game engine. In terms of features that are handled inside Unity, so we have the data access, SOFA data access. So it is in read and write mode. There's a support of GPU. There's also a SPH plugin that has been integrated, as well as the electrophysiological plugin. There's also some catheter and endoscopic simulation. There is a Geomagic plugin, and it's also possible to do some carving, drilling, some ultrasound rendering, and fluoroscopic rendering. So everything is more detailed on the movie available on YouTube. For the different release, the idea is to support the different versions of SOFA. So now it is possible to load SOFA from the 2012 until the 2112. And in the next week, I want to release the 2206 also. And for each version, we also have some different plugins that are supported. So everything is detailed on the website. I won't go into all the details here, as well as the details of the different license pricing. So there is some trial version, some academic version, as well as commercial license. Now I will speak more about the recent collaboration. So one what is start to be quite old now is the follow haptic collaboration. The integration of the follow haptic avatar device inside SOFA. So now it has been released beginning of the year. It's open source and NPL on the SOFA framework GitHub. I don't know what to call it, namespace. And it's compatible with the last two releases of SOFA on Windows. It supports multiple tools, so you can check on the website of Follow. It supports many different devices, so like Grasper, camera, endoscope, etc. You can use several devices at the same time with SOFA. And so inside SOFA, it has been modelized with articulated system mapping. So with the idea to be able to move in, to represent all the different articulation of the device, and you have some force feedback on all the degree of freedom as well as on the grasper. This is just a small movie on the integration of the two graspers inside SOFA and inside Unity. So just to interact with a deformable lever. Then there's a new collaboration with the company Apply Touch Technology. So it is another haptic device, which is, the goal is to be more portable with different configuration depending on the surgical intervention you want to address. Compared to compared to the TouchX, Geometry TouchX, the idea is that it can cover a wider area. It's really much lighter, and you have nearly the same force feedback. I put here the spec, but I won't go in all the details. You can check the website. So 6 degrees of freedom, 3 degrees of freedom for the force feedback. So it will be released soon. We still need to do some work on the plugin, because right now only the position is used. There is no orientation, and it has been tested only with a single tool. So I want to implement the several devices handling, and it has been tested against different deformable objects. There's another collaboration with LN Robotics. So coming back to the presentation by Professor Choi this morning, it is to simulate guide wire navigation. So inside SOFA using a beam adapter. So many contributions have been done on beam adapter to make it more usable, I would say. And on top of that, we are also simulating a fluoroscopic rendering. So both are SOFA simulation using beam adapter. Yes. I see time passing, so I will go through. Now, just very quickly, I'll speak about the different plugins also that are, so it's work done since several years, but they are being released this year. So the first one is mesh refinement plugin. So the idea is to be able to remesh tetrahedral meshes, and so you are able to do some cutting. So right now it's private, but we are considering releasing it in GPL. It's compatible with SOFA on all platforms and support user interaction and GPU. This is just an integration of it inside Unity, and so you can define a plan direction of cuts, and you can cut it. So this example was done on a flying lever, a big flying lever with 10,000 tetrahedra, sorry. And right now it's also support haptic interaction. So the scalpel is simulating using the geometric device, and you are able to do some cutting on a deformable lever. And there's still a lot of work to do to be able to really compute the penetration of the scalpel and to compute a nice and continuous cutting. And last, no, sorry, not the last. So there's a tearing plugin, so that Hugo just spoke about. So the idea is to be able to simulate some tearing simulation, but also peeling simulation. So to be able to, with user interaction, to tear the mesh and cut it. So it's compatible with SOFA, and it's a GPL, open source. There is a volume version that is coming also, but it will depend on the mesh refinement plugin. And I see the time. So last simulation is using an advanced version of the carving engine, where you can do some refinement, but also to perform other features like texture change. So right here we are burning the fat tissues. And so everything has been integrated inside Unity, and it's using a geometric device and simulated using direct solving. Okay, that's it for today. Thank you for your attention. You have all the contacts if you want to contact me or see the different repository, and just put the list below, sorry, so you can have access to it. Thank you.
Thank you, Erik. Is there any question? Is there any question in the audience? I see clap from many people here: Davide, Christian, Damien, and so on, Eleonora. So here, yeah, if anyone has a question, do not hesitate to unmute and join us like online. I'm sorry. Okay, rose the end. Okay, I'll try to find the. I don't have any more.
No, I think
somebody rose the. Did he raise the hand, or if? Please come on stage. Veronica?
No, but I think it's clapping only.
Oh yeah, it's okay. Do not hesitate to unmute if you are asking for if you want to ask a few questions. Paul, yeah.
Hi, Erik. Thank you for the talk. For the plugin that does the fluoroscopic rendering, do you also support introducing contrast agent?
Not yet. No.
Thank you.
Is it normally it's planned? Yes.
That's cool. Thank you.
So it's a stay tuned reply. And yeah, and basically I was writing here what kind of collaboration, because first how we can collaborate with Infinitec 3D, and who I mean if there is specific topic of collaboration you would be interested in.
As I said in the beginning of the slides, it's really to support the open source version. But the idea is if you have any simulation you want to do or you are not able to do because there is something missing so far, the idea is to be able to implement it, yes. And just contact Infinitec 3D to see.
Okay, I will add the contact in the chat as well if you like. So thank you very much, Erik. There will be time for discussion again with Erik after the 4 different sessions. Just for a reminder, so that's the schedule of this session, numerical methods and AI, where we started with Erik here, who will be in the room number 1, obviously afterwards, and again room number 2. There will be Martina, Paul 3, and Robin 4. We'll then now take the next presentation, which is from Martina Finocchiaro, located at UPC. Are you? Yeah, perfectly. We see you. You can actually share your screen, and then the floor will be yours to present your soft tissue simulation, especially on colonoscopy navigation.
Hi, Hugo. Hi, everyone. Thank you. Actually, this work was developed together with Ameya Pore, so he will start to present our work together, and then I will take the talk.
Perfect.
Okay, thank you, Hugo. Thanks, Martina. And good afternoon, everyone. My name is Ameya Pore, and I'm from University of Verona and UPC Barcelona. And I'm presenting jointly with Martina, who's enrolled at Scuola Superiore Sant'Anna in Pisa, Italy, and in UPC Barcelona as well. So the title of this talk today is Soft Tissue Simulation for AI-Driven Colonoscopy Navigation. Now, colorectal cancer, it's growing exponentially to become one of the most commonly occurring cancer globally, with approximately 900,000 deaths per year. And the risk of lymph node metastasis is limited if the lesions are diagnosed at early stages, stage 0, stage 1, which are suitable for endoluminal procedures. Otherwise, it requires major surgery and chemotherapy. So it is crucial to screen the lesions at early stages. Now, cancer screening is carried out through a routine colonoscopy procedure where the colon wall is inspected for abnormal tissue and lesion, and it may be followed by a polypectomy procedure such as the submucosal dissection in case a cancer tissue is detected. Now, clinically, colonoscopy is carried out manually, where an endoscope is inserted from the rectum to the end of the colon, or cecum, and then it is retracted back to carry out bowel wall inspection. Now, there are several drawbacks of this whole procedure. It requires multiple users to collaborate. There is a non-intuitive mapping between the tip of the endoscope and the steering knob of the endoscope. And this requires long and extensive training process, making this procedure susceptible to human errors such as tissue stretching and perforation. Now, platforms such as Strauss robotic system, there is EndoSamurai, Ease system, which are still in the research phase, not yet clinically approved. They have provided teleoperated control, which enhance some user or operator skills, providing more dexterity. So some very recent work on magnetic guided endoscope provides semi-autonomous navigation with minimal and discontinuous human intervention. So in general, current research efforts, they are directed towards increasing the level of autonomy for the navigation phase in colonoscopy, because it's a repetitive, time-consuming, and physically demanding phase. So autonomous navigation will place surgeon in supervisory role, allowing them to focus on the medical decision rather than low-level control execution of the endoscope. Now, one of the common approaches for autonomous colon navigation is to direct the tip of the endoscope towards the lumen center. Prior works have proposed some rule-based controllers to reduce the distance error between the image center and the detected lumen center. However, these algorithms fail when the tip of the endoscope is very close to the colon wall. And these situations occur due to the highly deformable nature of the colon, due to which lumen detection is not very trivial. And it requires adaptive exploration method to find the new direction of motion. So data-driven approaches such as deep reinforcement learning can provide some degree of adaptability. However, in the surgical domain, they have only been applied for low-dimensional state space, such as robot kinematic data, which are more trivial to learn from. Actually, the next talk lined up today by Paul will give you more insights about these problems. So the contribution of this work is image-based DRL approach using the same inputs as the human agents, that is through vision, and we call it deep visuomotor control. So DVC learns an end-to-end mapping between the endoscopic images and the control signal of the endoscope. So we define a standard Markov decision process where the agent receives the state ST and it outputs an action AT, which is applied to the robotic endoscope, and it takes the agent to a new state ST+1. So as a consequence, the agent receives a reward RT, and the state input which we use here is a downscale 128 cross 128 pixel endoscopic images, and the action space is discrete angular rotation values in the 3 degree of freedom of the endoscope. The reward function that we use here, it encourages the agent to minimize the lumen distance and penalizes in case no lumen is detected. And the policy here, it consists of convolution neural network followed by a recurrent LSTM layer, and we use a very consolidated algorithm called PPO, which is a very established deep reinforcement learning algorithm. Now, to develop the end-to-end joint training, we have developed a realistic colonoscopy simulator that I will let Martina take over and explain you more about it, along with the experiments and the validation that we carried out. Martina.
Thank you, Ami. Yes. So here we have, there should be a video of the, of the simulator. So the simulator, of course, is based on SOFA, and we use the Unity SOFA plugin from that Erik just presented to have this nice visual rendering. The organs, so the colon is 3D reconstructed from CT colonographies of real patients, and then we create the mesh and we apply the texture. We use a linear finite element method to produce the deformation of the colon tissue due to the contact with the endoscope, as you can see in the video. And the endoscope is modeled as a capsule, such the one that Ami just presented, which is magnetically driven. let's go to the next slide. Yes, so we decided to test the DVC algorithm in this simulation environment together and validate it against the navigation of 20 expert GI endoscopists. So we asked the endoscopy to perform simulated colonoscopy, robotic colonoscopy. We use 4 different columns. One column, which is the C0, is a simplified one and is used to train the DVC algorithm and also to get the endoscopy familiar with the controller. So we asked to perform navigation in the column from the rectum to the cecum using a video game joypad. Then we use C1, C2, and C3 to test the DVC algorithm and also to test the performance of the endoscopist, where C1 is slightly harder than C0 and C2, C3, they are actually harder than C1. So we asked the endoscopist to first perform the test in C1 and then either in C2 or C3. Here you can see a video of the teleoperated navigation of the on the left side of the endoscopist with the video game joypad, and on the right side you can see the autonomous navigation with the DVC, where the green spots represent the detected center of lumen. So we track some metrics to compare the performance of the autonomous navigation algorithm and the endoscopist. So first, the average distance between the center of the lumen and the capsule. We actually want the capsule to be as centered as possible in the lumen. Then the number of collisions between the capsule and the column walls, which we want to reduce because this is correlated with the pain that is caused in the patients during the procedure, and also the collision could cause lesions on the column. Then we also track the length of the trajectory and the time of performing the navigation. As you can see, there is a significant statistical difference in the DVC and the performance of the endoscopist in terms of distance between the capsule and the center of the lumen, and in terms of collision, which makes sense because our system was using a reward feedback based on the tracked center of the lumen. And then we also track the smoothness of the trajectory with the jerk index. And we can see that as the DVC has a pretty stable smoothness level, for the endoscopies, we have endoscopies with performed really smooth trajectory, while we have others that actually have not smooth trajectory at all. So it's really variable. Then once we saw that actually the DVC outperforms in terms of actually quality of the procedure, the endoscopist, then we wanted to check whether actually the cognitive load was less with the DVC rather than performing a manual procedure, which is important when you develop robotic solutions. So we actually asked 20 novices to perform the colonoscopy procedure in the simulated environment. Firstly, fully manually, so teleoperated control with the joypad, then with a rule-based control, and then a DVC, which was a supervised control. So we were asking the users to actually take the control whenever the algorithm was failing to find the center of the lumen. And then we asked to track their level of stress, or mental and physical stress in the NASA task load index. And we can see that actually the DVC was rated the least stressful, so was the one minimizing the cognitive load. So to conclude, what we did here is that we use our environment developed with SOFA of robotic colonoscopy to design, train, and test a DVC autonomous navigation algorithm, and to validate it against navigation of endoscopies in the same simulation environment. And also we use this simulation environment to check whether the DVC was actually reducing the cognitive load. Future works will be based on moving to testing from virtual environment to a physical environment with a real robotic system. This work was also presented at AROS in Japan, so you can find the full paper here at the QR code. Thank you.
Thank you. Thanks to actually both of you. Very nice presentation. If I understand correctly, so it's the DVC algorithm which is learning from images generated by the simulation, right? Okay.
Exactly.
That's very cool. Is there any question in the audience on site? Yeah, Vladimir. Yeah, just a second. There you are.
So thank you guys for the presentation. I have a small, I don't know, maybe it's too specific, but just a question: why did you opt to go with PPO and not say, I don't know, soft-actor or critical? Is there any specific reason for that?
No, actually, we tried with several hyperparameters, and the wall clock training time for PPO was relatively less compared to soft-actor critic or other recently developed more deep reinforcement learning models. So it's just the hyperparameter tuning was easier. That's why we selected this model. And the goal of this study was not actually to implement the state of the art on the DRL, but to show that we can use the simulator to train deep reinforcement learning algorithms. But I think I would like to mention here that you can find this the implementation open source, so you can integrate with a Python script and use any DRL algorithm that you want for the training.
That's pretty nice. Thanks a lot.
And for the links, is that on the slide? I can't see it. Could you share that later on in the chat?
Yes, definitely, yeah.
I'm sorry, maybe it's just me. Okay, it's maybe with the QR code, you mean? Yeah. Okay, thanks a lot. Is there any additional question? Yeah, Paul. So can you unmute yourself, Paul, maybe? Or
oh yeah, sorry. It was just a comment on the question before, where SAC works great if you find the perfect hyperparameter combination, and horribly if not. So if you have a resource-intensive training that has a lot of wall clock time, you're most of the time better off using PPO.
Cool. If any other questions, keep them for the breakout rooms that will come right after the 4 different sessions. We're gonna continue actually with you, Paul, and we're gonna keep talking about surgical robots and learning. I will let you present your work. So Paul is also, as you saw, one of the contributors of the SOFA Awards this year. Yeah, perfect. We can see the slide. The floor is yours, Paul. Go ahead.
Yeah, thank you. For those not there, like half an hour ago, again, I'm Paul Maria Scheikl. I'm a PhD student at KIT in Karlsruhe, Germany. I'm going to talk about surgical robot reinforcement learning in SOFA. And to start off, our motivation is always training artificial agents without a human in the loop in simulation, and then deploying them in artificial agent human-machine teams, so really collaboratively. The main motivation is that when looking at one of these surgical robots, we have many arms, but just one surgeon with 2 hands. So we have a lot of idle instruments. And we hope that we can train cooperative agents to take over the currently not controlled arms for an environment. For example, to adapt the camera view or tension tissue. Related work, you've seen one in the talk before by Ami. There's also other works done outside of SOFA, but very few of those are actually image-based, suffer the curse of dimensionality. So as soon as you try to control more than 1 or 2 arms, it's very hard. And none of them look at human cooperation, so interacting with human after having learned policy. Quick recap on multi-agent reinforcement learning, same loop as standard reinforcement learning, but now it's not one agent, but multiple agents that independently choose actions which are applied to the environment. And we tried that in one collaborative task where we had 2 completely independent PPO agents that had to solve this task of tissue retraction and touching a goal with the other object. So one agent was controlling this blue gripper that lifts a gallbladder up to expose a visual target that's currently like in the first step covered by the gallbladder. And then the second agent has to touch this visual blob to solve the task. And now we looked at what happens if 2 humans solved the team. So those 2 surgeons have Xbox controllers in their hand. One is controlling an environment each. Then we looked at, okay, what happens if we train that fully in simulation? And then, of course, the most interesting part, what happens if a human controls one of the instrument and then the learned policy controls the other one? And we're very pleased to see that that actually not only works, but also leads to, oh, that's some flickering, leads to some nice improvements. We looked at, okay, if we pair the human with learned policy, the task gets solved faster and with much fewer collisions. So it's an actual collaboration that brings a benefit to the surgeon. And then the next part we looked at is, okay, what happens now if we want to do sim to real transfer? So learning something in SOFA and then applying it onto a real robot. For this, we again looked at a simplified tissue retraction task where a robotic gripper starts in a random position, has to go to a known grasping point, grasp the tissue and retract the tissue to make this red dot visible. And that publication is currently under review. A training setup, as I've said, we want to train purely in SOFA and then deploy this image-based policy on the DDRK. And as you can see in these small, low-resolution GIFs, that actually worked, and we're very happy on that. And we hope that its review process is finished soon. So yeah, thank you very much for your attention. I was a bit quicker than expected, so we have more time for questions.
Perfect. Is there any question in the audience? Yeah, again, online. Is there anyone in the chat here? So yeah, Amy gave the link of the DVC algorithm we mentioned before. Is there any question for Paul online or in the room? Gavin, did you raise the end?
Oh, sorry, I was on the phone.
I'm sorry?
Sorry, I was on the phone.
Okay. Can you go on slide 10, Paul, please?
Yeah.
Just regarding the graphs, it means from my understanding, it means that like all the artificial team, like so both, so basically no humans in the loop would always be the like best and most efficient way to solve it. Is that because it was like trained on a virtual environment, and maybe due to that the on which actually the AI was trained, so it was like a bit biased, or do you think it would be the same if we would apply that yeah?
So I guess if we gave the humans some training time in the simulation, so to kind of learn the controls, learn some hand-eye mapping. So what happens if I push the controller into that direction? But of course, the artificial agents were trained for much longer. So they had an accumulated training time of like 60 hours, just of real time, let's say, not wall clock time. And I guess if a human trained a similar amount of time, they would converge towards this optimal artificial behavior. But one thing that is really difficult for humans is estimating depth in this 2D scene. So if you look at the video, you kind of can estimate how close the instrument is to the liver or the gallbladder by looking at the shadows, but still it's very hard for a human. And an artificial agent just had learned, okay, if I see these visual features in that combination, I'm at this depth. So that was much easier for the CNN, basically, compared to a human who has to really learn this depth mapping.
And do you think that, for instance, in the interface you would have for surgical purposes, like adding that kind of I know I think Fred, you worked for a time on that, for augmented reality view, where you could actually help with some fake colors that are actually projected on the organ or stuff like that, to actually give really an idea of depth to a user, a human user, so that it can improve its sensation of depth. Yeah, I don't know if this could help.
Yeah, it's a very nice idea. We have tried having two channels, so the RGB image on one side and a depth image on the other side, but that was rather confusing for the user, like trying to look left, look right, and then estimate between that. But if we could overlay that, or in the perfect world, have a nice augmented reality setup, that would definitely help.
I got a question in the chat, but I'll take yours afterwards. We have time for questions, so that's what matters. Which would be, what are the next actually step and scenario that you're planning? I got the exact same question on my own notes. It was what basically would be the other tasks than like pulling and finding a target. Is there other stuff that you are targeting?
So right now we look at creating a whole suite of reinforcement learning environments that can be open sourced, published in order to kind of do more robotic reinforcement learning research for surgery, but not by like doing one publication on one environment, then throwing that away, looking at the next one, but having a good set of standard reinforcement learning environments similar to Sofa Gym, but from a surgical perspective and not from a soft robotics perspective.
That would be really cool to have like a basis shared with one that others could compare to, and so on. That would be nice. Another Paul has a question for you, Paul.
Yes. Hi. Thank you for your presentation. So the two tasks that you've presented, you've got two agents, two different agents. No, on the first one, sorry. The second one, this was a unique agent where you grasp and you show the red dot. So for this task, you've trained two agents, but it seems to me that the tasks are very. There is no interaction between the tasks because there is for the, I will call it the green agent, the time that it comes to the white dot. The other one will have finished its task of removing the yellow the gallbladder. So does it work if the green agent is on the path of the blue agent, meaning that because you said that they are uncorrelated during their training or something like that. I don't remember clearly, but is there can they interact? And so there is a second question with that, is that at the end you've presented the hybrid team with the human and the and so again somehow the autonomous agent had to remove the gallbladder, and so he did it, and the human was able, for instance, to wait if he didn't achieve it. But if it was the contrary, does it work with the contrary? If the human is too long, does the green agent wait for it or not?
Thank you for the question. Yes, the task that we look at right here is very sequential. You can kind of start in a phase and only look at one of the tools. But we also tested what happens, for example, if the gripper moves in a way that it would collide with the catheter, like during training and during evaluation with the humans. So the second question. And that actually works. So for example, if the catheter tries to go towards the tool before the target is exposed, and then the gripper moves towards the catheter will try to move out of the way such that the gripper can move without colliding with the other instrument. And we tried that in multiple configurations, and it was actually pretty hard to kind of fool the trained agent. The only thing that did not really work is when the human agent was very, very, very bad at the task. So with this independent learning, of course, one of the agents sees the other agent as part of the environment. And if the agent is good and trains more and more and more, that works quite nicely. But it, for example, has never seen in its recent past very, very bad behavior. So if you, for example, take the gripper, stay at the same position for a very long time, and then move towards the catheter very fast, there can be unpredictable behavior. Yeah. I hope that answers the question.
Yes, thank you.
Okay, thank you.
Thanks a lot. I see there is another question on the chat from Maxime, but I suggest we move on because we're still a bit away from time. But Maxime, if it's fine for you, keep your question for the breakout room, and it will be room number 3 for Paul. if it's fine. Otherwise, I mean, I would be happy to connect you later on if you need it, if you're willing to. And we'll conclude this first session and we'll stay with AI. So it was I mean, it was the dedicated session, even if there can be AI application and usage in other work later on today. With a platform that has been recently developed and released called DeepPhysX, developed at INRIA by Robin. And Robin will present you this entire platform developed in Python, and that you could in time use definitely. So the floor is yours to talk about DeepPhysX.
I have connection issues. So maybe I will use
Okay. So we will try screen sharing. All right.
Oh, I am not connected again. Okay.
I'll let you know when we see the screen.
Okay. No.
It's coming.
It's coming, I think.
Perfect.
Yeah. Thank you. So I am. Is that me? How do I check? Yeah, I think it might. Okay, sorry for that. So let me go back to my slide. Okay, sorry for that. So I am Robin Enjalbert. I am from the Mimesis research team located here in Strasbourg. So I am an engineer dedicated to the development of DeepPhysX, which is a Python framework aiming at interfacing deep learning with numerical simulation. So I am here to make this technical presentation as an introduction to this framework, but I will also present my recent developments on another Python library, which is called Simulation Simple Database, also called SSD, that is dedicated to data storage in general for your numerical simulations. So as you guessed, the presentation will be divided in two parts, the main one focusing on DeepPhysX, and the other part will be focused on SSD. So DeepPhysX is a full Python framework dedicated to interfacing AI with numerical simulation. Basically, it is an easy-to-use interface that handles your data generation, training, and prediction sessions for deep learning. In the following slides, I will go through details for all the features for each pipeline. As you can see on this diagram, the project is very modular. It is divided in several packages. The main one is the core, and we have additional layers that ensure compatibility with external framework. So with this architecture, we can possibly be compatible with any simulation or AI packages. So for now, we have a compatibility layer for SOFA and PyTorch, but it is really simple to integrate another one if you want to use another framework. DeepPhysX was released about 6 months ago, so you can easily install it with the Python package installer. And I also spent a lot of time in designing tutorials, examples, etc. on the GitHub repository. There is also a detailed documentation if you're interested. So about data generation, so basically DeepPhysX will handle all the data that will be involved in your deep learning sessions. So when you generate data from your simulation, DeepPhysX will create a database to store all the samples from your simulation. You have several modes for your database depending on your activity. And you can find all the basic features that you may need when using datasets for deep learning, such as data normalization, data shuffle, etc. What you see in the animation is a visualization tool that we include in DeepPhysX, so that you can have a visual on your simulation while running the data generation. Sorry. Another cool feature with DeepPhysX is that you can launch several instances of your simulation to parallelize your data generation. So what we do basically is to use a client-server architecture. Each client will handle simulation. This simulation will produce samples. These samples are sent to a database, and then from the database, we can retrieve all the samples to create batches to feed the network. And all of that is controlled with a TCP/IP communication protocol to synchronize the server and the client. So that's it for the data generation. Now for training, we have two training modes. There are two ways to train neural networks with DeepPhysX. The first mode is offline mode, which means training your neural network with pre-computed datasets. And the other one is online mode, which means generating data while training your neural network. So with this mode, we try to keep as much versatility as possible. So it is really simple to customize the data flow between components. The components, I mean the simulation and your network. And it is also possible to customize your data operations at each step. We included a tool to visualize the evolution of your training progress with TensorBoard, which is automatically launched when you start a training session. And with the PyTorch layer, we are also providing two network architecture for now, the full connected architecture and the UNet. But as I said, it is quite simple to integrate another one if you want to use another network architecture. And finally, once you trained a neural network, you may want to use its predictions to drive your simulations. So here you have two examples that you can find on the GitHub repository. So for these examples, we trained neural networks to predict the deformation of objects with hyperelastic materials, given a force as an input. And so, yes, you can try this demo. They are interactive, so they are pretty cool to manipulate. And all the required data is stored online and will be automatically downloaded when you launch the scripts. So you see that these demos are running with the visualization tool provided by DeepPhysX, but it is also possible to run your prediction in the SOFA graphical interface. So my latest developments was about including some features with SQL database in DeepPhysX. These features were not really implemented in DeepPhysX actually, but in an external library. The reason is that these features are really useful for physics, but could also be useful for people that are not doing deep learning. So this is why I created an external library, which is called Simulation Simple Database. And we use two databases in DeepPhysX. The first one is dedicated to the training data, so to make the link between the network and the simulation. And the other one is used to register the visualization object, so to provide the visualization rendering of your simulation. So I will now switch to the SSD overview. So this is a Python library that provides solutions to store your data from your numerical simulation and to also visualize them. There are two parts in this project. The first one is dedicated to storage of any data, and the other one is dedicated to the storage and the rendering of visualization data. As you can see, the project architecture is quite the same as DeepPhysX. So we have core packages and a layer to ensure compatibility with SOFA, so that the project is also modular. And this one was released about 1 month ago, and it is quickly installing with pip, and also you have examples, tutorials, and documentation online. So we'll go to detail for the storage part. With the storage part, you can, in a few lines of codes, define your own database. So I mean, you can create any table you want in your database, and for any table, you can create any data field. So you have several data types that are available to create these data fields. And once you created your database, it is really easy to read and write data in this database. I added several additional features, such as merging database, exporting database in other formats, which can be useful. So that's it for the storage part. And the other part is a visualization package. So this one is dedicated to storage and visualization of visual data. So you have the same idea. Visualization data will be stored on a database. So you can visualize your data in live, so while your simulation is running. But as your data will be stored on the database, you can replay your simulation after you run your simulation. So we provide a factory which allows you to build various object types, such as meshes, point clouds, arrows, etc., with at least customizable rendering style. You can draw them wireframe with different color, with color maps, etc. And to build and render the objects, we use the Vedo Python library, which is a VTK interface, basically. And finally, about the SOFA layer, so you may all have recognized the caduceus example. I added some small additional features. So you can record SOFA data. This data will be automatically loaded to the database at each time step. What I did not mention before is that without this feature, you have to manually add data at each time step. With this feature, you just have to register the data at the beginning of your script. With this layer, you can use both tools, so the storage tool and the visualization tool, with the SOFA graphical interface or with a Python interpreter. And so it makes a good solution to drive your simulation with Python, but still having an off-screen rendering of your simulation. So all of these animations are taken from demos that you can try for yourself if you want. So that's it. I hope you enjoyed this presentation. Feel free to try those projects and to share your experience with it. And thank you for your attention.
I was going to ask for actually the exact comment for the installation of DeepPhysX and SSD. So that's perfect. I don't know if the slide. I can see the slide perfectly on my end. I know the screens here are getting it for you as well. Okay, cool. So is there any question for Robin? Leonora? Thanks a lot. Ciao. We can't hear you. No, we can't hear you. You seem to be you're not muted indeed, but it may be just the mic option. I'll let you know as soon as we can hear you. I have a question just for really basic, people who know nothing about training and so on as I do. How could I actually have a simulation from SOFA which runs in SOFA and so on? Sorry, I can output, I can train it with different forces and so on. How can I actually what kind of output, or how can I actually use DeepPhysX when I just have my either Python or XML scene? Does it work also with XML or?
Actually, no. It works with Python only, okay. Since you have to create a compatible simulation with DeepPhysX, and you have some functions that you have to implement. So create and how to define your training data. So yes, you have maybe some things to change for your simulation, but the changes will be quite a few. And
you can test your mic anytime, Eleonora.
Can you hear me?
Yeah. I'll ask another question afterwards. Please go ahead, Eleonora.
Okay. Thanks, Robin, for the talk, and I'm very happy to see that DeepPhysX has been released. I have a question about the data generation and the simulations. So, which kind of simulations do you support? For example, can you implement in DeepPhysX simulations with multiple objects, or are you at the moment tied to a single geometry and input forces?
For now, we only focused on one geometry per simulation in the research team, but it is yes possible to use several objects in your simulation. It depends on your application, but it is perfectly compatible with any kind of simulation.
Okay, so do you see it quite straightforward to include also like constraints and collisions, or do you think it will require a huge effort on top of what's already there?
No, I don't think so.
Okay, well, optimistic.
yeah, I'm quite optimistic with that. Yeah.
Okay, thank you.
All right, so I'm gonna just I guess there is maybe other question for Robin, and there will be time right now for actually asking them directly in the breakout rooms. So that was for this first session of the afternoon on numerical methods and AI. You'll find Erik in room number 1. You'll find Martina in room number 2, Paul in room number 3, and Robin in room number 4. I'm gonna create them actually right now. I'm just checking. Okay. Yeah, they're actually already created, so that they were actually open for lunch, so they are still here. I'll make sure that everyone can actually join them, and yeah, please feel free to join everyone in the different rooms to ask questions. Thank you a lot, and see you back in the main room at 2:50 p.m. CET. Guys, can you see the poll active here? If you click on the bottom right corner, the three dots in the interface, and then there should be a polling. Can you see it, Damien? And is that active for you? Because apparently it's some kind of ended or closed.
C'est écrit qu'il n'y a aucune question posée pour l'instant concernant.
Okay. Sorry guys. Apparently there is an issue with the polling system of WebEx. All right. Apparently the rooms got closed, so the time is over. I see someone with the camera within the room who got activated. All right. I see. Tanguy, you took the lead, right?
Yeah.
Okay. Cool. So we tried during lunch to set up back the poll, but I mean I don't know if we are getting this feature of WebEx to work, but we'll see. I'm sorry. Sorry. We're gonna start the second session of the afternoon, which will be the second session on soft robotics, and we're gonna start with a presentation of Tanguy on direct and inverse modeling of soft robot by learning a condensed FEV model. We'll continue back to Chile then with Stefan, and there should be also Gavin, I think, co-presenting. Then Canada with Audrey, who will present the soft robots learning to crawl. And finally, we'll get back to France with Adrien presenting the usage of framework for multi-robot control of deformable objects. So we'll start with you, Tanguy. If your sound is good, if the slides are perfectly visible, we are exactly on time, so we can restart. The floor is yours, and obviously for everyone in the audience, please get ready for the questions after Tanguy's presentation. Thank you.
Thank you, Hugo. So hello everyone, I'm Tanguy Navez, so I'm a second year PhD student under the supervision of Olivier Goury and Christian Durier at INRIA. So today I'm going to introduce our recent work on learning a condensed FEM model and its of soft robots and its application to direct and inverse modeling. So there are several ways to model soft robots, and our choice for FEM comes from its precision.
Sorry, Tanguy, can you speak just a bit less loud? I mean, your sound is perfect, but I would say too perfect, okay. and some people are getting are blooding from the ears here in the room. Sorry about that. For once, we have a very good mic working on your end. Sorry about that. Yeah, go ahead.
Is it better now?
You can like make ASMR sound. It would be cool. Even a bit less louder. So sorry for that. Go ahead.
Okay. Yeah, so our choice for using FEM models comes from the fact that they are usually the most precise in the literature, but at the cost of being computationally more expensive. Yep. So our motivation for learning our motivation for learning condensed FEM models comes from the fact that first, its use for soft robot control is difficult for non-specialists of numerical computation, as the computation needs to be optimized to make it real time. There are a lot of hyperparameter and modeling choices to make. The second argument is that soft robot FM representation is characterized by many parameters, namely edges and nodes. And so through running more compact representation, we can use it in control application more easily. Finally, gradients are not readily available for FEM in SOFA. And so through running compact representation of a robot, we can obtain a differentiable link between output and input matrices. And so we can then use it in a differentiable optimization framework for design or control. So what exactly are we learning? We're learning a mechanical representation of a soft robot based on the FEM. And so this mechanical representation takes the form of two matrices. So the first one is compliance matrices compliance matrix projected in the constraint space, and the second one is a free displacement matrix. So as an introduction example, I'll show you this diamond robot. So this diamond robot is actuated by 4 cables that can be pulled from its center, and we control the position of its end effector. So in the simplest form, we have 5 constraints. So 4 for the cables and 1 for the end effectors. And so this compliance matrix represents the coupling between the different constraints, whereas the free displacement matrix represents the free displacement when we don't consider any of these constraints, when we don't consider the constraints. So we can use both these matrices for direct and inverse modeling of soft robots, and I'll show later how we do that. So first, how do we compute this condensed FEM model? We first have a step of data acquisition, during which we sample in the actuation displacement space. So for this robot, it corresponds to the space of the different length of the cables. Once we acquire the data, we can train multi-layer perceptron for prediction. So this MLP takes as inputs the mechanical matrices when no actuation is applied on the robots, as well as the actuation displacement we want to apply, and it predicts the mechanical matrices once the actuation displacement is applied. And so for training this MLP, we use the following laws, which is the sum of the element was now 2 difference between the elements of the data acquired matrices and the predicted matrices. So once we train this MLP, we can use it for inverse and direct modeling of soft robots. So first, I'm gonna introduce how we usually do the modeling in SOFA, especially for those who are familiar with the soft robot plugin. So we solve the following quasi-static equilibrium when we have on the left side the stiffness matrix and the displacement of the node, and on the right side the external forces such as the loads, internal forces coming from the elastic energies, and finally the effect of the constraints. So we solve it in 2 main steps. So the first main step is to solve for a free configuration of the robots, and then we add in the second main step the effects of the constraints. So we first compute the compliance matrices projected in the constraint space, as well as the free displacement matrix. Then, if we're interested in inverse modeling, we can solve for the actuation using mathematical programming. So usually we try to reduce the distance between some effectors on the robot and some goals. And so once we find this actuation, we can apply it, and it's followed by a corrective motion. And so we do that for each time step. So in our framework now, to use the MLP, we will apply step 2 by a prediction of the matrices instead of computing it at each time step. So as application, we applied this pipeline on 2 robots. So the first one is the diamond robot I already introduced, and the second one is a gripper robot that is made of two fingers. So each finger robot is actuated by 2 cables, and we control the position of its tip. So as results for the diamond robot, so we try to perform this trajectory for the evaluation. So this trajectory is basically a circle around the position of the end effector. And so here you can visualize part of the trajectory with the that we performed for the evaluation with the computation, the computed FEM model, and the one using the land model. And here you see a projection of the trajectory in the XY plane. So you see that we can match very closely the trajectory of the that with the land values that we obtain with the computed values. As a second example for the finger robot, so here it's just to show that we can match the trajectory of the FEM model with the land model, but what we are interested in is to transfer the mechanical representation learned for single finger robots to a gripper robot that is made of 2 fingers. So here the setup changed a bit. For the inverse problem, we use an inverse problem based on the coupling of 2 fingers. And so we try to maintain a constant distance between the tips of the 2 fingers. And so it's made to mimic the manipulation, to evaluate the manipulation of an object. And so we see the results that you obtain with our of learn model. So to finish, by some discussion, so we show in our work that we can use condensed FEM representation for the control of soft robots. This kind of method that is data greedy, and so it's hard to use it when we have a lot of constraints. So we plan to consider active learning methods in the future to sample data in the most interesting regions in regards to reducing the error when predicting the matrices. Finally, this learned MLP is a low memory cost model, so it could be easily integrated on a small embedded microprocessor. So we plan to do it in the future. And 2 last points, we also plan to add contact management because actually we don't consider any contacts. And to use this learned mechanical representation gradients in application in design and control code optimization. Thank you for your attention, and don't hesitate if you have any question.
Is there any question online? And please, if so, unmute yourself because I can check also for the hands that got rising here. Right on time, by the way, Tanguy. To me, I mean, it reminds me of some work which are also conducted at Mimesis at like using some networks for inputting, I think, some initial guess as in some solvers. Here, if I understand correctly, you're trying to automatically some kind of build the compliance matrix. Is that correct? From the delta free that you are having, so the interpolation distance or velocities?
Yeah, we're trying to build only the constant matrices, and so to avoid computing all the FEM at each time step.
Okay. When you say the whole FEM, it's when trying to avoiding just to build the whole W function, so to invert the A matrix. I mean, the system matrix.
Yeah, to do the product of the matrices when we compute the W and the W.
Okay, and this is what you call the mechanical representation, right? Okay, cool. Okay, I don't know how it could actually. I got the feeling, but it's really because I'm not involved in both projects, that it's some kind of close to what some other guys like Alban are a bit doing. It's so I don't know if you know what they're doing, like in the Mimesis team here located in Strasbourg. So that's I could let them know about what you're doing. That's That's I think it's pretty close. Is there any question else in the audience or in the chat? And can you get back to the slide where there is the the round, the round, the circle? Yeah, okay. Go ahead. The circle, the circle trajectory. Yeah. Could you just explain briefly, or your interpretation of the error, the difference due to when using the learned values? Do you have any idea, like where it could come from the data set that you used for training, or?
We learn a matrix, so we don't have the exact same matrix. We have a very close matrix at the end, so the error could come from that, but also from some numerical error.
Okay. Okay.
You see that we can match. We can't even match. We can't match perfectly the goals with the computed values. Also, so it could come from numerical error, but it's super minor.
Another question from François. Okay, come closer.
Yeah, thanks for your presentation. Just one quick question. I don't know, do you think like the method you presented, it's general when it comes to the material parameters you use for the EFM, or is it just for linear material law? It can actually converge to the correct result?
It's a question I never asked myself. I don't know why it wouldn't work.
No, another maybe unrelated, but somehow I don't quite get what is the result of the data acquisition path or that you described. Is it you acquire many compliance matrices from a different displacement set from your initial configuration?
Oh, yeah, if I'm going back to what we use for the training, when we do the data acquisition, we acquire many mechanical matrices for different actuation that we apply on the robot. And so that's what we use. But this mechanical matrices depends on partly on the materials that you choose. So I don't see why it wouldn't work with other materials.
Yeah, but maybe my intuition around that, but maybe I'm completely wrong. It's just like, as far as I understood, like these matrices are acquired from the displacement you apply is already starting from a rest configuration where you have zero potential energy. So is that correct or not? Like, or is it incremental? It's just like, I think like if it's the material law is nonlinear, then you don't have like I don't know, balance forces between your internal and internal forces and the actuation you actually apply. But maybe it doesn't matter. It's just
yeah, it doesn't matter. One of the interests to use MLP is that we can learn something that is not non-linear. And for a question, we give as input the two initial matrices. So if these matrices change because of the material law or reason that users gave, these matrices we would learn also for these matrices in our MLP.
All right. Yeah, thank you very much anyway.
Thanks a lot, Tanguy. And directly, Stefan, incoming for the second presentation of this last soft robotics session. It's going to be Stefan talking about sensors, actually soft robots that are actually used for sensing, and in that case, sensing in order to evaluate errors and disturbances. So I'll let you, in direct from Chile, introduce us the work you have been doing with so far.
Hugo, hola a todos. Can you hear me well?
Yeah, we can hear you well. Just for the moment, the screen sharing here, at least, is not. I don't know if others can see that. Can see the screen. Damien, can you see the screen sharing already, or for us it's black? Yeah, it's full black.
No.
Oh, hold on. Should we use? Hold on. Let me see. Oh, is this better? Yeah, I think
it's loading.
Yes.
Yeah, perfect.
All right.
Perfect.
So yeah, so thank you, Hugo, for the introduction. So I would like to talk about this work which has been recently published at Aricò, so it's basically the same presentation. It's a collaboration with a PhD student and the lab at ETH in Zurich. And they have already designed a pneumatics-based soft actuator featuring 2 segments. And the work was based around modeling this soft actuator or soft manipulator using SOFA, in particular also including the fiber reinforcement. And then we addressed some challenges such as calibrating the simulation to the real manipulator. And we also prototyped some tasks such as hands-on teach mode, meaning, for instance, that you can take the robot arm and put it in a certain configuration, and with the help of SOFA, we will find the actuation needed to keep it in this configuration. So these are kind of features that we know from rigid robots, but are still being studied for soft robots. We also did some experiments on estimation of forces at the tip in a completely static or at rest configuration, or also by the configuration inflating the chambers. So this is a quick overview. We'll go more into the details in a second. So as I mentioned, this is a robot platform that was already existing and was published in the year prior, in 2021. And there's a design it's similar to what Paul Chailloux presented this morning, regarding that we have some fiber reinforced chambers with a core surrounding a core that allows for the passing of instrumentation and tubing and so on. And in its first iteration also it has included a bend sensor to get information about the bending radius, and the model that was employed was for the geometrical part, it was approached with piecewise constant curvature, and then it had for dynamics a rigid body approximation, lumped rigid body approximation for calculating the dynamics. So when transferring to SOFA, we had this same or the familiar approach that is the use for in the statics-based modeling. So we have the linearization of internal elastic forces at each time step, and we have static force equilibrium. And in particular, what is interesting again is the use of constraint-based modeling. So we have a vector of possible constraints, which in our case has 2 components. One is concerning the pressures inside the chambers, and the other one is concerning external forces applied to the robot arm. This is, oops, sorry, the overview. Sorry, what happened? Oh, sorry, I think somehow I need to go back. All right, so yeah, we have these 2 deformable segments, and each one is separated by a rigid segment, and this time it is equipped with optical markers, from which in the optical tracking software we obtain poses at these rigid positions. And there's the fiber reinforcement, which are just modeled as springs that surround the perimeter of the arm at certain intervals. So this is an approximation for the fiber reinforcement, and it's just adding rigidity in the radial direction, so that this is also to prevent in simulation the expansion of the chambers. And so in terms of model-based sensing, we use the inverse modeling-based approach to include the sensor information. And it means, I just will talk briefly about this, is that as I mentioned, for each segment, we are observing the orientation with a sensor. So in this case, it's the optical tracking, but the idea is to use IMUs to get inertial frame information. And if there's an external force happening on either one of the links, the two frames will change their configuration. And this is what's encoded in this relationship here that we can obtain using the compliance. So we can find what is the relationship between a change in constraining forces using the compliance with respect to the change in orientation. So this is this function here, omega, is just mapping each node to its orientation, and its partial derivative with respect to the node motion is indicating how much the orientation is changing when we have a node motion on the arm, on the manipulator. And this is, in SOFA, this is expressed as angular velocity in 3D. So then when solving the inverse problem, this is solving this optimization problem, we can find the changes in forces and efforts that minimize the difference between the orientations expressed in the model with respect to the one sensed on the real robot. And so the important part here is that we have a constraint optimization, meaning that we use the information about the real pressure inside the valves to constrain the problem. And so basically, we have 6 pressures for the 6 chambers, which are known values, and the 4 possible forces, so 2 per segment, are the ones that we are interested in. And first, we are, as I mentioned, we worked on the calibration, which means in this stage, we let SOFA estimate the pressures inside the chambers that will yield the configuration that is closest to the one observed from the camera tracking. This will allow us to tune the Young's modulus of the robot and potentially also the stiffness of the fiber reinforcement springs. So basically, what we wanted is to have a unit conversion between the input pressures observed from the valves and the values estimated in SOFA. So basically, if the pressure estimated by SOFA was too high, so that would mean that in the model we have to reduce the stiffness or reduce the Young's modulus. And this was an iterative process. So in the output is that there's unit pressure between the real world and SOFA. Then the next, so here we see some results for the calibrations. So for the details, you can look in the paper. So overall, the configuration is achieved with a error of approximately 15 to 20 degrees, which is reasonable. Of course, we always wish it to be better, but for now it was working nicely to provide the desired interactivity. And it's also there's also some more work to be done with respect to the sensing part as to improve the pose estimation. But this is, I would say, a nice proof of concept. For the teach mode, we also showed that this was working for a variety of different set of configurations. So again, actually, in this time we have a lower error, and it's due to a subtlety in how the arm can reach the configuration, that this is working with a little bit more robustly than the calibration. We can discuss this further in the discussion if you're interested. And next, we did some disturbance estimation. So basically, I have a comparison with ground truth with respect to external applied force. And here, it turns out that this can work nicely in a certain force range, as you observe here. So this is, in this particular experiment, it's not very large forces, but it also turns out that you have to recalibrate the arm. So we're still looking into how this is related to the FEM model and how, for instance, how it is affected by the use of the number of nodes or all the different aspects of the modeling. So it's showing that it can be done, but at this time it requires to make some compromises. So as I mentioned, inside the measured force range, it's quite accurate. But as I mentioned before, it does need its own calibration. And this last experiment was performed. So instead of pulling on the arm, now the arm is being pressurized, which this exerts a force on the force sensor, and we can also get a good estimation for the force. All right, so I thank you for your attention, and I'm happy to answer questions. I don't know if I'm on time. No, I'm not. Maybe.
Yeah, a few minutes away from timing, but no worries, Stefan.
Yeah.
Congratulations.
Thanks.
Is there any question for Stefan in the audience? I'm checking the hands. Yeah, I'll let you, Fred, tell me if you see some people raising the hand. In the room, do not hesitate neither. I got a few here. Yeah, you mentioned that you were evaluating the U modulus and the stiffness of the springs of your model. Based on I did not exactly get this point. It was in some in some experiment here exactly. Can you explain exactly how you did that here?
Sure. Yeah, that's it has sometimes you have to switch back and forth between different points of view. So in this case, at the calibration stage, we know the pressures that are being measured in the valves of the real robot, right? But there's no correspondence to the force, so the pressures estimated in SOFA to reach certain configurations. So in this configuration, so in this setup, we use the inverse model in SOFA without any external disturbances, and we we observe the arm using the tracking system, and SOFA will calculate the pressures that minimize the difference between the estimated configuration in SOFA and the real world. I don't know if you can follow.
Yeah.
Okay.
Yeah.
And sorry, I saw some glitches in the images. This is why I was asking. So basically, then you get a geometric correspondence between the two, right? So kind of like what you see here. So you see that there's a geometric correspondence between the models, but it is possible that if the SOFA model is not tuned correctly, that the pressures here could be much higher than what is actually being applied on the real robot platform. So that means that we have to tune the stiffness in the simulation to the point where the conversion is 1. And so you see if I apply one.
Is that done? Is that done automatically? Are you minimizing it yourself, or I guess it's not manual tuning that you're doing?
It is. It was manual for this work.
Okay.
So it requires a few iterations to converge.
Okay. Okay, cool. A few other questions, but since we are running out of time, I would join you in the room and ask the question afterwards. if you don't mind. And if there is anything, do not hesitate to leave comments in the chat again. And otherwise, thank you again, Stefan, for your presentation. And we will then move a bit more northern from where you are and have Audrey, I think, in the audience that I just uploaded, made applause. Yeah, perfect. Welcome, Audrey. You should be able to share your screen and share your presentation. I'm going to make sure that the timer is actually getting started, what I did not do properly for you, Stefan. Sorry about that.
Okay. Hi. Thank you for listening to my talk today. My name is Audrey Sedal. I am an assistant professor at McGill University in Canada. This is work that I did jointly with Charles Schaff and Matthew Walter from TTI Chicago. This work was published in RSS in June, and the title of it is Soft Robots Learn to Crawl, Jointly Optimizing Design and Control with Sim-to-Real Transfer. So I'll be explaining what all those things are and what we achieved. I'll actually begin with explaining what we have achieved here. So what you're going to see is a baseline kind of crawling robot. I think many of us have seen this robot before. It's a canonical robot of soft robotics now. It has these legs, and it learns this, or it doesn't learn. It does this, kind of inching gait based on out-of-phase movement of the front and hind legs. In the lower left corner here, you can see a sofa simulation that we've built that shows this behavior as well. So if you say to someone, design a soft robot that does locomotion, this is probably what they would think of. It certainly is what I would think of. But the question that my computer science colleagues posed is, could an algorithm think of something better? And here is the robot that we actually found. So the first thing we can note is that in our episode of 20 seconds, it travels twice as far. So where the baseline robot traveled around 5 centimeters, this one's traveling over 10. And also that it learns this interesting kind of pivoting behavior where it exploits these differences in friction between when the contact surfaces of those legs is larger or smaller. And that in general, our learned robots exploit asymmetry in order to go, again, a little bit faster. So I'll go ahead and pause this here, and we'll actually go back to our #1 learned robot and just go through this again. So it's learning this behavior where it pivots, and then it kind of snaps forward. And what you can see is that in the simulation, this is happening as well. So how are we going to actually get an algorithm to learn this robot? There's a few kind of ways that we framed this problem. So what we were thinking about doing here is optimizing across a joint space of both a robot's control and its morphology all at the same time. Why would you want to do this in soft robotics? Because in general, you have a lot of different degrees of freedom that your material can deform around. You have lots of different materials or actuation strategies that go with those materials. And so if you could search all the possible morphologies at the same time as all the possible controllers, you might end up with that robot that has the best of both. Some drawbacks to this, right, is that simulation of deformable materials, like we know from SOFA, is generally slower than simulation of rigid-bodied robots, and that some things about the physics of these materials can make sim-to-real transfer difficult. So keeping this in mind, that we have this larger space to work over, where it would be good if we could search across it, but we also have these drawbacks. So our work actually addresses both of these things. The first contribution that we make is an efficient reinforcement learning based algorithm that does this co-optimization in both the design and the control space. The second contribution that we've made is a technique to speed up finite element simulations that's based on model order reduction. So I'll explain both of these in a little bit more detail now. So our reinforcement learning framework, it kind of does what you would think for the traditional reinforcement learning for the control section, except that the control policy is always conditioned by the design. So what does that mean? It means that in parallel, as we update our control policy, we're sampling and resampling from a large distribution of possible designs, some of them are shown here, to try to get the probability of a high-performing design higher overall. And by conditioning the control policy over the design distribution and continuously updating that design distribution with every transition, we're able to look for something that might be the best in the joint space. So of course we used SOFA for our modeling. We know that this is a highly accurate finite element simulator. Something I say to robotics people all the time is that finite element is the method, the computational method for modeling deformable objects that has been validated for almost 100 years now. And so this is, if you have a background in mechanical engineering, you want to be doing finite element to get an accurate simulation. I don't think anyone's going to disagree with that at SOFA Week. But the problem we encountered is if we just ran this plane, it would be too slow for this kind of semi-supervised RL algorithm. So we used model order reduction from 2018. I'm sure many of you are familiar with it, to speed it up. The one problem with this was that applying this kind of a reduction was infeasible for a large set of designs. Because if you have to reduce every design in your distribution individually, and if there's over 7,000 designs in your distribution, which was the case for us, then you might not really be gaining a lot in your learning. So what we decided to do instead was to reduce the parts of our robot. So to modularize our design space and reduce the legs for the robot and the central disk for the robot's body, thereby creating a library of reduced parts that we could actually combine in order to create new designs. And so for a crawling robot design space, this actually worked pretty well. You can see here we have perhaps different kind of snapshots of our leg, our soft pneumatic leg moving. We have different snapshots of how the body might move. And we actually collect the data on entire robots, but we sort of zoom in on specific components as we're doing that. So by applying it in this way, by modularizing it, we were actually able to create a very large design space for relatively little time spent doing model order reduction. And so anytime we can restrict ourselves to building a robot from a set of parts, this approach might be possible. So we did some experiments here. What you can see is that we actually constructed our robots that got learned through our semi-supervised method in SOFA. So as we searched over the placement of new nets, as well as their assignment to a different pressure regulator, which is what controlled how much air pressure was going into each pneumatic leg, we were able to find these best combination robots. So we asked, how many legs should the robot have? Where should they be? And what pressure should be inside each leg as time goes on to produce the best gait? Some results from our learning are actually shown here. We have around 1 million training steps here. And what we have on the y-axis here is the amount of forward progress that the best robot in that episode of the distribution was able to achieve. So as you can see, kind of at the beginning, we have robots that can go a few centimeters. Keeping in mind our baseline was able to travel around 5 centimeters. Around 400,000 training steps, we see this sharp increase in excess of how far the baseline was able to go. And what it turns out is that our best robot is going to make around 10.4 centimeters of progress. So what can we say about this robot that was learned in comparison with the baseline robot that actually I, with a PhD, having studied soft robotics, designed? What can we say about it? Well, the first thing we can say is that, yeah, it goes twice as far. It goes more than twice as far in simulation, and it goes twice as far in real life. The second thing we can note about many of these learned robots, almost all of which exceed our baseline in performance, is that they leverage some asymmetry. And we think that the reason why they have some asymmetry both in their bodies or perhaps in what pressure regulator they're attached to, and thereby have asymmetry in the actual actuation, we think that they leverage this to kind of pivot and to reduce their friction overall with the floor. So I'm going to go over these results one last time, just to show, again, the contrast between the kind of symmetric gait that a roboticist would think of, and then a more asymmetric gait that actually turns out to achieve better by doing these pivoting type motions. The other thing that we can keep looking at here is that we actually have the SOFA simulations of each of these. If in the question period you want to see more detailed comparisons and results of the simulation versus the real, I'd be happy to share those. But yeah, it turns out that I think 3 or 4 of our learned robots do outperform the baseline. So robot 2 achieves 6.6 centimeters in real life. And yeah, we have all of these kind of unusual asymmetric gaits that we were able to learn. So yeah, I'll go ahead and show the rest if there is time. For now, I will say thank you. And I will note that I, in the mechanical engineering department at McGill, am looking for graduate students. So any prospective graduate students can feel free to contact me at the email listed. Thank you.
Is there any question in the audience? I thought, as I wrote in the chat, I thought about Etienne, who could be interested. But is there anyone that would like to ask a bit more details, or who would have a question for Audrey?
Yes, I would have a question, Hugo. Can you guys hear me? Yeah?
Yeah, go ahead,
Okay.
Stefan.
I was looking at the video and I was wondering if when you have this pivoting effect, which makes the crawling more efficient, it's because you have less, you have a smaller area of contact between the front leg compared to the back leg. So somehow you're reducing friction between the back and front legs. Is that something like that in the end that works?
That's my best hypothesis right now. So I will show you why I say that. We track the center of the robots in simulation and in reality. And on the right-hand side here is the graph where we can see the center of the winning robot over time. And so I think we get 2 things with the pivoting. The first thing is this part where it slides back. It actually doesn't slide backwards as aggressively as the baseline robot does. It has these little parts where it kind of slides back to go forward, but it's not as bad. And then the second thing that you get out of the pivoting behavior is this explosive forward motion. I hope you can all see my mouse, but we see these kind of spikes up and then a soft sliding back at each cycle of the gait. So in addition, I think, to reducing the friction contact, which I think is part of it, it also puts the robot in a situation where it kind of can snap forward into a new stable configuration a little bit faster and with more power.
Okay. And the related question, I mean, in your approach, so you're trying to optimize the design, but because it's FEM and complicated problem, you sort of create a set of possible scenarios, right? You create shapes where you have the legs in different configurations, and somehow the reinforcement learning algorithm chooses what is the most optimal configuration out of the ones you've created, if I understood correctly. If you wanted to go one step further, which is really to have an algorithm able to propose, a more optimal design, for instance, optimizing the shape of a leg, how would you address this?
Also, I think our, our main idea here, which was to reduce the parts rather than the entire robots. So, reduce one leg and then attach it. I think if we wanted to do, if we wanted to use this approach, we'd have to think of how to modularize the leg. That said, I have seen other work that does look at, for instance, they look at optimizing the shape of pneumatic pockets in this type of actuator. And they actually, I think, have, I don't recall if it's discrete or not, but they have a design space that actually has gradients in it that they can search over a little bit more easily. So I think, if I was really asked to do that, I would maybe go in a different direction than this modularization of the entire space. This is really great for kind of system level, but not for specifics. if that makes sense.
Yeah, thank you very much. Great work.
Thanks very much.
Thanks a lot. Thanks a lot, Audrey. There were actually other questions, including one from Olivier himself, from the model order reduction, who you know. Let's, as I asked you, if you can keep your question for the breakout session right afterwards. So it's like in it's going to be in 15 minutes right after Adrien presenting the fourth and last presentation of this second session. It will be awesome, so that we keep track on time, and there will be anyway questions in the breakout room. Thanks a lot. Thanks, yeah, again, and thanks a lot, Audrey, for the presentation. And now we make the loop back to Europe with you, Adrien, and you will be presenting a work that has been a collaborative work done with SOFA for shape control, multi-robot actually control of deformable objects. I'm eager to see the multi-arms robot controlling soft objects. Go ahead, Adrien.
Thank you for your introduction. Hello, everyone. I'm Adrien Koessler. I'm an associate professor with LCFC Lab in University of Lorraine in France. And I'm going, as Hugo said, talk about multi-robot shape control of deformable objects. First of all, let me also mention the colleagues who helped me a lot on this project, which are Paul Baxic and Adrien Courtecuisse from University of Strasbourg, eCube and team Mimesis, and also Thibaut Rarijon, who is working with me at University of Lorraine. So first of all, I will give a brief overview of the contribution, and then I will dive into the details of how I'm using SOFA and how we made it to the real robots, to the real experiments. So first of all, the context of deformable object manipulations is that such flexible objects are encountered in a large variety of contexts. So it can be in the industry for seal assembly, cable manipulation, cable routing, or tasks like this. Also in households context, deformable objects are everywhere. And we can also mention textile processing, which is very important in the field and gives rise to a lot of contributions. So the idea of controlling the shape of a deformable object is that you have multiple grippers on the object. You have a shape that is defined by the position of several material points on the deformable object that you are trying to manipulate. And you want to find motions of the actuators that deform the object so that the shape of the object reaches a desired value. And you can write it in a mechanical fashion where you have to minimize an error and make it converge towards zero. So in comparison with soft robotics, I'd say that the system of the two robots manipulating a deformable object is like a bit of a weird soft robot, where we have, instead of one end effector, we have multiple points for which we want to control the position. Our actuators, they are well, rigid robots, industrial robots that we have. There are not many of those actuators grasping one of the objects, but those actuators are have full degrees of freedom. So once you see past those differences, you can think that there are similarities in terms of the control problem formulation, and that obviously we can use the same tools for modeling and simulation. So in the literature of deformable object manipulation, shape control is generally presented as a problem of linearizing the relation between the poses of the grasping robots and the shape of the object. So here appears a Jacobian matrix that we want to estimate. Because if we can estimate this Jacobian matrix and invert it, we are able to write a control law. So this is very common in many contributions about deformable object manipulation. And there are many ways to estimate this matrix that I call the interaction Jacobian matrix. It can be using model-free method or sensor-based method, or rather model-based method, be it learning, simple deformation heuristics, or mechanical models. And as in the community, in the SOFA community, this is where we are positioned, since we use finite element analysis. So a simple overview of what we are doing to present some specificities of our work is that we have two robots that grasp the object, but one is a leading robot and one is a following robot. So one acts like a perturbation and the other one is tasked with the problem of recovering the desired shape of the object. And also something that is new is that we use a vision system to close the control loop and to avoid problems with modeling errors that I will talk about in the experimental analysis. And so yes, this is the experimental setup that we have at the lab in Metz in France. So two industrial cobotic arms that are manipulating the object and the camera, the RGBD camera in the middle of them. Okay, so what's the usage of SOFA in this context? So I recall the control law that I presented before. So the control law is basically made of 3 elements. We have the interaction Jacobian matrix that we want to invert, or to pseudo-invert actually. We have a gain matrix that we need to set for the control purposes, and we have an error vector that we need to find. So what we assume in this work is that for measuring the error vector, we use only the vision system to perform this, and to estimate so the interaction Jacobian matrix that relates the change in shape with the displacement of the actuators. That's where we want to use SOFA to perform inverse simulation. And to estimate this Jacobian, we are using finite differences, which has been already introduced in previous work, so like the work of Paul from Strasbourg, team INRIA, Mimesis, and eCube on needle steering, robotic needle steering. So the idea is that we introduce small perturbations for each degree of freedom of the actuators, and we see what's the resulting change in shape, and we perform those finite differences one by one to populate the Jacobian matrix. So this method has to be run at least, so in our case, 7 times for each time step. So we need to assess experimentally if this is feasible. But we already have ideas that it can work because inverse simulation has been used quite extensively for control. So both in soft robotics, in medical robotics, and also for open loop deformable object manipulations in several works. So the tricks for computation that we are using and that Paul implemented are related to the solution of the constraint problem. There are tricks like preconditioning, not computing all the matrices at each time step of the animation loop, and also having a method to regularize the pseudo-inverse of the Jacobian matrix in order not to have problems when computing the control law. And the SOFA implementation for this, so we have mostly used custom components and a custom animation loop that we cannot share at the moment because there are joint efforts for dissemination. But you can build an offline equivalent of this procedure for computing the Jacobian matrix using bilateral constraints and Python controllers, so very simple structures in SOFA. And the controller loops also handles the communication with ROS. So because we get the robot poses back from ROS, we also get the shape that is being monitored by the real shape of the object that is being monitored by the vision from ROS. We get the inverse Jacobian from the animation loop, and then we can compute the control law and send the velocity that we want to send to the follower robot back to the ROS controller, from SOFA back to the ROS controller. So looking at the experiments, we are using 2 universal robots UR10E cobotic arms with industrial grippers mounted off them, and we are using the official ROS drivers supported by universal robots to make this work. The deformable object is a sheet of foam that has been painted, and we have put adhesive markers on it for the visual tracking. So it has a very simple model, so linear elasticity and co-rotational modeling with 1400 tetrahedra, and we have performed characterization in tensile testing to estimate the mechanical parameters. The vision system is as simple as it gets, I'd say, because it's a low-cost real-sense RGBD camera that we use, and we have used also a very simple algorithm for the feature tracking. And this is why I took a screenshot of how the programs that I'm using begin, is because Python does magic, and SOFA Python 3 in particular does magic, because when using it, you can basically make a SOFA and a ROS communicate very easily. So let me show you what it looks like on the real setup. So we have the left robot. The left robot is the one that's the follower. So it's tasked with recovering this shape despite the other robot moving. So as I input motions on the interface. And we can see on the left side of the screen what it looks like in the SOFA GUI. So here we can see that despite the motions, which can be both translations or rotations, motions of the leader robot, the follower robot is able to place its effector correctly in order to maintain the desired shape. So overall, I'd say that the experimental detailed analysis has shown that there's a following error due to the reactive nature of the control law. This is obvious, but still we can see that the control law converges despite difference between the real shape that is being perceived by the vision system and the shape that is being estimated by SOFA. And we also have sufficiently high FPS for simulation in order to use this in the control law. So in conclusion, I'd say that the main takeaways are the successful hardware and software implementation, the quality of Jacobian estimation that is sufficient for what we are doing at the moment, and that the control shape is quite robust, in particular to modeling errors or to sensing errors. But there are still some limitations. I will not deep dive into it. More interesting are the future directions. So the future directions, there are two main directions, I'd say. First one is having multi-robot manipulation in a symmetric context where there is no leader, no follower, but the robots are just cooperating with all the degrees of freedom to bring the shape to a desired value. And also something that interests me in particular is to replace one of the objects with a human and see how the human deformable object robot system can perform manipulation. So thank you for your attention.
Thanks a lot, Adrien. It's nice to see. I mean, I noted a few things where I got really the feeling that there is possible connection with several work, at least the one from Tanguy that has been presented a bit earlier, same for Paul. So that's why I was also poking for questions in the audience. Is there any question here? I guess not you, Paul, here, but if there is anyone online who would like to ask a question, I already got one from Louis, who is asking, Adrien, does your simulation takes into account the feedback from the camera in the control loop, or is it just used to obtain the ground truth in order to estimate the performance of your system?
It's neither of the two, basically. It's an intermediate solution. So I'm showing back the block diagram because this is where we have the answer. So actually, you can see that the output of the feature tracking, it's not related with SOFA simulation. The output of the feature tracking, it allows to define the shape error. So it allows to define the error vector that is being used in the control law. But at the moment, SOFA does not see what the outcome of the vision system is. And so this is also something that we could address in the future. We can imagine non-rigid registration, which is quite extensively investigated within SOFA. But at the moment, it's not the case. It's not directly used in the SOFA simulation, the visual information.
Thanks a lot for the answer. Any other question in the audience? I did not see another one right after Louis, but do not hesitate to write it in the chat. Otherwise, you can keep it obviously for right now in the breakout room. I would have just a very small one. That would be, what would be the main reason, the main explanation, in your opinion, why there is a delay? You know, while you are actually moving the robot, the master one, and why the other one is actually taking a bit of time. Where does this delay come from?
I'd say that a delay was expected because it's a very simple proportional control law. It has there's no anticipation in the control law. It's only a purely reactive control structure. So I would say that having a following error it would be expected. Also, we could not go very high in the dynamics of the control law are not very high because of stability problems that we need to address.
On the simulation point, you mean? Or on the simulation side, you mean? Or about
no, I mean
stability?
the whole the stability of the control law. Not that of the simulation. The simulation is quite stable. We didn't encounter such problems, but the stability of the control law can be a bit of a problem. So I'd say it's expected, and that maybe we can think about other control structures in order to reduce this delay. But it was expected.
Cool. Yeah, thanks a lot. I would have others as well. I will have to split in the different breakout rooms right after. So just for the reminder, so that was for this session here. The program ending with you, Adrien. So you'll be room 4, Audrey room 3, Stefan room 2, and Tanguy room 1. I'm gonna open the breakout rooms actually right now. There we are. Okay. I'm gonna open them. Yeah, and I'm gonna move the speakers as well. So Adrien in the room number 4, and I'm gonna move also the other ones. In the meantime, so it's gonna be again a 20-minute break. We're gonna restart in 20 minutes in the main room for the last session. And stay tuned. They're gonna be augmented reality, digital twin for surgical simulation, open source needle insertion simulation from the US, and finally we'll conclude with the award ceremony. So thanks a lot, and see you in the breakout rooms. I'm sorry, apparently some rooms seem to be locked. Okay, no, it seems it's okay. Okay. See you in about 15-20 minutes.
Hey, how are you?
What is that presentation?
It's SOFA Symposium. So the software that we're actually using for doing the planning, well, simulating the soft tissue deformation, it's in SOFA. And then every
Hey,
year
Lydia.
we post this really big. I am so
You're
sorry.
not muted.
I'm sorry.
No worries.
I'm sorry. I'm excited.
Sorry, Lydia and Mario, there will be like 100 seconds left in the breakout rooms, and then the whole session will restart here in the main room. Okay, people will get back
Okay,
here.
perfect. So, okay, so this
See you
is
in a-
where I should be waiting.
Yeah, see you in a sec.
Okay, thank you.
Hi guys, I guess everyone is back in the main room. I'm gonna just check that here. Breakout rooms, yeah, they are well closed. Just a few words. So it will be the before last break before we actually close the vote for electing the best contribution to the SOFA Week Award 2022. So just if you did not do that yet so far, just go to sofaframework.org/SW22/vote and you'll be able to elect what's your favorite contribution of this year. The result of the vote and of the jury election will be given at the end of this last session. So this last session, sorry, up here I'm taking my notes, is the second actually about biomechanics and medical simulation. It's my pleasure to welcome the three last speakers, Mario, Lydia, and Veronica, that will come one by one on stage. And it's going to be a mix of startup presentation, research presentation, and as you can see, there will be augmented reality, as I said before the break, digital twin, and with augmented reality possibly in the surgical context, needle insertion, and catheter simulation with Veronica. So it's going to be again broad topics of medical simulation. We're going to start with Mario. Mario, I think you're already ready, and you can already like share your screen if you can. Let me know if there is any problem. And as we already did so far, there are going to be like about 10 minutes per presentation, 5 minutes of questions, and after the three presentation, this time we're going to have a small break and closing the symposium day. So go ahead. If you can share your presentation, Mario. Yeah, apparently it's loading. Perfect. I can see that on my back screen and the front screen. Go ahead, the floor is yours.
Well?
Yeah, perfectly.
Okay, thank you. Thank you so much. So good afternoon, everyone. So this first presentation is going to be the startup one. So I'm going to present you the entrepreneurial project Twinical, which means twins surgical. So we are building a medical product for digital surgery to ensure better outcomes for surgeons, hospital, and patients. And in particular, what we want to do is to harness the complexity of deformable organs, also thanks to what SOFA has developed, what the SOFA community has developed over the last few years. So our mission, as I said before, is to optimize the patient's medical outcome by guiding surgeons throughout the surgical journey. So you can see here three keywords. So the first one is optimize, which in our vision means to improve something by taking into account the hospital and surgeon constraints. So we have to bring technology and to integrate it seamlessly so that it can be really useful for surgeons and for patients. So the second word is guiding. So the technology we develop is meant to assist surgeons during the surgical journey, which is composed of two main stages. So the first one is planning the surgical operation. So there is a thinking process to select the best surgical strategy to treat a disease. And the second one is the proper execution of the surgery. So as you may already know, so surgery is a complex act, more or less invasive and risky. So what we are going to do in our project is to identify, prioritize, and reduce any surgical risks for soft tissue surgery, and in particular for liver, as you will see, by providing surgeons and clinicians with quantitative digital information. So far, we may say that surgery is quite artisanal act, which means that there is a lot of information around, but is not usually available. So what we're going to do is to provide surgeon with what we call digital twin-powered surgical GPS, to enable a patient-specific, accurate, real-time planning and navigation system for soft tissues. So during planning, what the standard method is, like I take standard CT images, which are a stack of 2D images describing a volume, and surgeons usually think of the strategy just by looking at those images, which contain a lot of information, but not easily available and readable, and usually takes expertise to read with ease those images. So in our project, we are going to build a digital twin of the organ, in this case the liver, as you can see, which has to be 3D, deformable in real time, and interactive. And we used to think of the digital twin as a common virtual frame for shared thinking, so before the operation and during the operation. So you can see that we have two examples. So the center image, we compute the entire 3D model of the liver from CT images, and then we can interact, in this case, via tactile screen, or we can use augmented reality glasses. What's important is that the digital twin is at the center, and we can interact with it like with any piece of technology that is suitable and available. So once we have the digital twin, we bring into the operating room, and we use the twin as the main navigation frame during surgery to provide accurate real-time navigation, which can be used in open surgery, in the left-hand side image, or laparoscopy. So in this case, as you already know, there is the presence of the endoscope is the main digital eye of the surgeon, and we exploit images to build the augmented reality framework. So the goal is to guide the surgeon's gesture, increase the accuracy of the resection. For example, when treating a tumor, we have to ensure that the margins are respected to prevent recurrence of the same tumor in 2 to 5 years. And also there is a very important concept of surgeon's workload, because it's very tiring to operate in laparoscopic settings, because we usually have 2D vision and we need to infer the 3D. There is limited space for action, so bringing the digital information can greatly reduce the surgeon's mental workload. So as I said before, the first application is going to be the liver cancer. So in this case, we have a great technology. We need to find a proper market to actually commercialize, deploy the technology, and actually exploit it. So liver cancer is, so the epidemiology of the liver cancer is quite concerning. So there are more than 1 million cases per year, not counting liver metastasis, which are 20 to 50 times more. And the post-surgery mortality rate can range from 6 to 10%. So we can see there are obstacles to the optimal surgeries. And what can Twinical do? With our software, we aim to protect, in this case, the liver functional segments and foster tissue regeneration, protect the structure of the vessel, which is very important for perfusion and drainage, and also ensure that the resection margins around the tumors are respected 100%. So today, we build a medical software which is local and targeted, which means we are going to install software into the operating room for liver surgery. But in the future, our long-term vision will embrace something that is transversal, connected, and robotized. So transversal across different surgical specialties and different types of soft tissues, connected by embedding cloud and edge computing technologies, and robotized because we are willing to integrate robots into the surgical workflow, because a digital twin is the perfect mate for the digital twin of the robots. So far, the project, this is the founding team, which is composed of 4 people, as you can see. Me, it's Mario, and Erik Pernod, as you know, a person you know very well, and Stefan as well, which is the head of the Mimesis team, and Erik Viber, which is our key OL. It's a liver surgeon which helps us on the clinical side. So far we have been awarded like iLab, I would say, great prize, Grand Prix iLab 2022, and we will officially kick off the startup in March 2023. So this is a broad overview of the project. So if you're interested, if you want to join, if you have inputs or people who might be interested in joining entrepreneurial adventure, please contact us, and see you later if you have further questions. Thank you.
Thanks a lot, Mario. I was actually I just wrote this question. It was directly at the beginning of the presentation. I wrote, yeah, but what would you be looking for? Maybe hiring. So again, definitely, if you are looking for position and here in like making the gestures of surgeons, like going towards simulation application and so on, do not hesitate to contact Mario directly. What I wanted to say as well is, what kind of are you looking for? Also, like academic collaborations and also maybe industrial collaborations with partners on specific aspects, or for the moment you're like developing the whole technology by yourself?
So for now, the technology we have is the result of a technology transfer from the Mimesis Mimesis team. And so we are actually, the SAT is helping us in packaging the core prototype and have it transferred to the startup. So the first phase is going to be focused on more on the development side, so bringing a prototype to an actual product which can be used. But I mean, we are always open for collaborations to actually carry out more research and advancing useful tools that we can actually install into the operating rooms.
Thanks a lot. Is there any question in the room? So my timer tells me it's very perfectly. It was perfectly in time. Is there any question in the room or in the online audience? Please do not hesitate to unmute yourself. I'm going to check again for the hand that could be rising here. And yeah, and you mentioned like hepatic surgery. Is that correct? Yeah. Is there really a specific surgery in hepatic surgery or a specific gestures that you are actually targeting, like removal of a part of the liver or ablation? Or
so for now it's going to be a mostly open surgery and laparoscopy for primary and secondary tumors of the liver and gallbladder. So in particular, we have 2 case studies of primary tumors and metastasis coming from colon cancer mainly, but ablation is not the primary target.
Thanks a lot. When it comes maybe later on to ablation, do not hesitate to again get back to us. Is there any other question in the audience? Not here. Online. And there will be, again, just as before, we're going to set up this time only 3 rooms for the 3 speakers of this last session. And obviously, Mario will be available in the room number 1.
All right.
Thanks a lot, Mario. We're going to move on with a second presentation. And we're going to move from an organ, digital twin, towards not only the organ, but also the needle that will be stimulated with Lydia. And we move from Paris directly to Baltimore, if I'm correct, for University of Johns Hopkins. The floor is yours, Lydia. You can actually share your screen. And I'll restart straight away the timer. There we are. Whenever you're ready.
That's not it. Do you see the screen?
Yeah, perfectly. Yeah, perfectly.
Okay.
Thanks for presenting
perfect.
today, and the floor is yours, Lydia. Go ahead.
Okay, perfect. Thank you so much, Hugo, for the introduction. I'm really happy to be here. Just very briefly, I am a PhD student with Dr. Axel Krieger here at Hopkins. And we also have a wide range of collaborators without whom this work would not have been possible. And we recently started integrating SOFA into our research workflow. And because this is my first time being here, which I'm really excited about, I'm also going to take a little bit of time to introduce the vision of our lab and what kind of research we conduct. So we are part of the Immerse Lab, and we primarily focus on smart autonomous robotic surgeries and medical devices. Surgery, big market, obviously, as all of you are aware. And the drawback is that most surgeries are performed manually, which means that surgical outcomes are heavily dependent on the operating surgeon. And now, obviously, that had led to an increase in robotically assisted surgeries, which are primarily in the form of teleoperated surgeries. And we've seen an increase in minimally invasive surgeries, but we unfortunately have not seen a proportionate decrease in complication rates and an increase in patient benefits. And really that's because surgeries are still teleoperated. We're not seeing that much autonomy for a lot of different reasons. And essentially our vision of a smart surgical system would consist of several items, one of which is augmenting critical portions of manual surgery with robotic precision for increased autonomy. The surgeon could then take on supervisory role for some technically difficult task, for example, suturing. On top of that, we're heavily interested in providing the surgeon with the highest quality diagnostic images during the surgery and prepare them for the most realistic plans and give them all the information that they need to make sure that they conduct the surgery safely. This is hopefully going to be reducing the variability, reducing complications, accelerating the learning curve, and enabling new surgeries and things we could not have thought of before. So obviously with soft tissue surgeries comes a lot of complications, which are mainly related to the soft tissue deformation. and the unpredictable shape changes that happen. So as you can all, think about it, your preoperative planning really does not match your intraoperative setting for a lot of different reasons. And that makes it really hard for performing autonomous surgeries, specifically on soft tissues, as compared to more rigid structure surgical systems. So some of the research that's conducted in our lab, I guess what we are mostly known for is supervised autonomous anastomosis, and that is short for STAR, which really stands for Smart Tissue Autonomous Robotics, autonomous robot. And essentially, this procedure consists of KUKA robots, and that the study was published in Science Translational Medicine in 2016. This is essentially a robot that's equipped with a custom suturing tool. And then we have another robotic arm that has an infrared camera to be able to identify suturing locations. On top of that, we also have a magnetically steered robotic suturing systems where you can have a tetherless needle perform various suturing tasks and even more complicated tasks using magnetic fields. And lastly, we even consider patient-specific implant design, where my colleagues would use medical images of a heart and then extract the 3D shape of the heart to design patient-specific grafts. And then they're typically optimized. They're obviously patient-specific, but they're also optimized to minimize wall shear stress and optimize the blood flow through the graft itself. This is just like a brief overview of the lab, but I guess the main topic of this presentation is the needle steering modeling inside of soft tissue. Why we're interested in that? We're interested because of prostate biopsies, and prostate biopsies come from prostate cancer, which is not good. So one way to identify whether the patient does have a prostate cancer or not is to essentially steer the needle through the template inside of the prostate, collect tissue samples, and then figure out whether that region is tumorous or not. Typically performed under ultrasound, but the preferred way is magnetic resonance imaging because it can allow us to visualize tissues that are potentially suspected, that have potentially suspected lesions. And then the most common technical challenge for targeted biopsies is the accurate placement of the biopsy needle in the suspected region. And although we do have robotic systems, with that can allow us to do the insertion, that is still not enough because we have a lot of other challenges associated with the procedure, as shown on this slide over here. The first thing is that the needle used for getting the biopsy is bevel shaped and it's flexible, which means it's really soft. It can undergo a lot of bending. That creates complex needle tissue interaction, and that generates extra deflection, which needs to be accounted for during the insertion process. On top of that, the prostate deforms heavily during the insertion of the needle, which means that the preoperative planning does not really match the intraoperative setting anymore. As you can see in figure A and B, this is the prostate before and after the endorectal needle guide insertion. It looks pretty different. So on top of that, it's a multi-layer problem, which means that the needle has to traverse a lot of different soft tissues before we can actually get to the prostate. So there is complex needle tissue interaction, which varies from organ to organ. And on top of that, the different organs deformation is also affecting the final needle position. So what we are using SOFA for essentially is to try to improve on the targeting accuracy of our procedure, whereby we would have a preoperative targeting, localization, and registration performed at the beginning, which means we identify the target points in the prostate that we want the needle to get to. And then we essentially match the physical setup that we have with the SOFA simulation in terms of boundary conditions, geometrical shape. And then we run the SOFA forward simulation that will essentially model the needle interaction with the different soft tissues and then predict the needle deflection within the tissues, which allows us to send the needle entry information back to the robotic system where we can do an intraoperative full needle insertion. After we do the intraoperative needle insertion, hopefully we have reached the target location that we're interested in. But as you can imagine, we have a lot of factors that can affect the final outcome, mainly the soft tissue properties and the needle properties, which are really hard to obtain very accurately. So after we perform the insertion, we can extract that information from 3D CT scanners for now in our experimental setup, and essentially use that to fine tune our simulation parameters, and then run the cycle back again, where we identify new target locations and run the SOFA simulation and then perform the insertion. So this is just a very brief overview of the different components in SOFA. I guess the most important part here is the choice of the models that we're using for the needle as well as the soft tissue. So for the soft tissue, we're using a co-rotational model, and it's often represented by the position and velocity of a set of connected nodes. And for the needle, we're using the Koessler model, which essentially makes use of reduced coordinates, which would speed up the computation time. And that allows us to get the best of both worlds, essentially. For our experimental setup and validation, we create our own phantoms. Maybe they don't look exactly like a prostate, but this is more so of a preliminary work and a proof of concept at this point. We're representing the prostate with a cylinder, and then the cylinder is submerged in different layers of soft tissue with varying mechanical properties that we can measure. And then the insertion is performed using a linear X and Y stage and a Z stage for the phantom. And everything is being registered under CT, under a 3D CT scanner, so that we can register the phantom with respect to the needle, identify the target locations, and then finally validate our approach by extracting the needle shape. This is just a close-up view of the entire setup before the needle insertion, and after the needle insertion, we can see that there's a substantial deflection in the phantom, with some markers over here for registering the entire phantom. And I guess this is more so of a preliminary work at early stages. So right now, what we're working on is applying constraints dynamically at various needle sections, so that we can then solve for forward kinematics. We then want to validate our simulation using our experiments, and finally to run the entire setup on a phantom with embedded targeting beads, so that we can really demonstrate how SOFA can be used to improve the targeting accuracy for the specific prostate biopsy application. This is just to put some faces on all of those names. These are our wonderful collaborators. Again, none of this work would have been possible without them. My email is over there if you have any questions. We have some references over here pertaining to the entire presentation. And yeah, I think that is it for me. So if anybody has any questions, I will be happy to try to answer them.
That's accuracy from the US side with a close to 3 seconds exactly the 10 minutes. So very nice timing. I don't know if I'm not sure I catched it in the entire presentation. I would say I just want that to be repeated another time if you said it. All the needle insertion part here that you saw, which is in development, as you said, Lydia, is like based on Koessler. Koessler is open, and the simulation insertion is also something that is and will be made open. So I think that would be really a good place to like gather all the experience on needle insertion if it can be. So yeah. Is there any question? Yeah.
Koessler is just to give credit to those who have been actually developing the plugin. So Koessler has mainly been developed by Yunus. So he's the main person who's been working on this, and Paul has been of immense help for putting everything together. And if you need more information, this is actually the GitHub link for the Koessler plugin. That is, I don't think it's the final thing is out there yet, but there's some preliminary work, particularly pertaining for soft robotics, if anybody is interested. So,
thanks a lot, Lydia. We've got already a question here in the room, but I'll check also in the chat. There is none for the moment in the chat, so there will be one. You'll see actually on the video. So Paul is asking a question. It's not your Paul. It's another Paul. Go ahead.
Hello. Thank you for the presentation. So you've tested your model on a homogeneous phantom, but the prostate is known to be a very heterogeneous and with a lot of well, I don't have the word, but it will lower the deflection of the needle actually, And how do you plan to cope with that in a real prostate? Because if you fine-tune your model on a homogeneous phantom, it will have a lot of difference with the reality.
Yes, you're right. And these phantoms are obviously homogeneous. And right now we're modeling them as homogeneous phantoms. So there's a lot of work to be done on that end. But as I mentioned, we are intending to run experiments on so if it does come to it, when we run experiments on a real patient, then we can extract the information from the patient itself and maybe find sort of an average way of modeling the prostate and averaging out the non-homogeneous properties into a single homogeneous property, and then trying it out. We're obviously going to run experiments on that before, probably using animal prostates. And we'll just have to see if that assumption is going to be valid enough. And if not, then we would want to consider incorporating more complicated non-homogeneous model of soft tissues in the SOFA process. So, right now, this is essentially more of a proof of concept for just getting the workflow together. And even though this may not look like it's easily directly translatable into a clinical setting, we're first trying to validate different aspects of the modeling, like the needle tissue interaction. And if we can check off certain boxes to make sure that at least the very basic simulation is running, then we can take on additional tasks and consider other approaches for a more realistic simulation. Does that make sense? Yeah.
Yeah. There was a thank you that Paul just said. Yeah, and I wanted also to stress the point that here again, it's something which is what I really love to hear about. It's like Germany, France, US collaboration. I mean, I don't care about the country, just like it was an easy collaboration because it has been made quite naturally, I think. So I mean, and it could be even like more open because you mentioned some electromagnetic control for I think it was for like suturing or I saw wire control, so could be linked to a former presentation made by Quentin from ETH. So it was maybe too early for you in the US, but everything is recorded, so you could access the presentation again. It links as well to the presentation of Insimo with the suturing simulation. So I mean, yeah, there is still, I think, many doors open for collaboration on this topic. So do not hesitate to first join Lydia in the breakout room in about 15 minutes, and even for later on, just to get in touch. So that's also true for the people in the room. Maybe Claire and Paul, you would have further things to discuss with Lydia in the breakout session. Thanks a lot,
absolutely.
Lydia. Thanks a lot for the presentation.
Just to like validate your point, this is one of the reasons why we decided to put introductory slides about our lab here, because we're always open to collaborating with people. So we'd be more than happy to get in touch with those who think that there could be room for working together.
Thanks a lot, Lydia.
Thank you so much.
It will be then the last presentation of the day, and it's actually the second participation, I think, from Veronica at the SOFA Week. You were already there last year. I think not as a presenter, but you were already there last year. And today we're going to have an augmented reality presentation. I mean, yeah, a presentation involving augmented reality in the context of catheter simulation, which is definitely a trendy topic because there have been already several presentations about catheters today. You can share already your screen,
yes, sure.
And I will reset the timer. And whenever you're ready, we can get started for the last presentation of the last session.
Okay.
Right?
Now,
yeah, we see the PowerPoint. Perfect. Yeah,
okay.
Great.
Okay.
The floor is yours.
I
Go ahead,
start.
Veronica.
Yes. Good morning, everybody. I am Veronica Rozzi, and I am a PhD student at Politecnico di Milano. Now I'm going to introduce you the work I developed during my master thesis, and it is a project which is part of the EU-funded Artery project that I developed with my colleague Paolo Vassena and our tutor Maria Chiara Palumbo. It is titled Integration of Real-Time Simulation and Augmented Reality for the Catheter Monitoring During Percutaneous Procedure. The Artery project will progress the field of percutaneous treatment, and in particular, the use case considered in the first part of the project is the mitral clip procedure used for the treatment of mitral valve regurgitation. The device is merely composed by a miniaturized clip and a delivery system. which is a complex system made by a multiple knob manually manipulated by the operator to advance and deploy the clip on the mitral valve, controlling the position and the orientation. The monitoring of the catheter during navigation from the right femoral vein to the vena cava relies on the use of fluoroscopy. However, the resulting images are only bidimensional and they don't show any detail of soft tissues, and more importantly, fluoroscopy is based on the use of X-rays, exposing all the people in the room to radiations. The goal of this project is to provide a more intuitive and radiation-free solution to monitor the advancing and the vessel interaction of the catheter during the intravascular phase by showing its holographic counterpart through an augmented reality interface updated in real time through a FEM simulation. The simulation is implemented in SOFA, and the main requirements are the stability, the tissue biomechanics accuracy, and the computational cost optimization. A physical sensorized catheter is developed within the Artery project. The distal tract of the real catheter is equipped by a FBG and EM sensor that allow to provide a virtual point cloud of its shape through a shape sensing algorithm. So in this application, we always refer to a problem where the catheter shape is known in real time. The information is exploited as initial condition in the simulation, and since it is entirely displacement driven, no mechanical model is required for the catheter modeling. In fact, the virtual model consists in a series of consecutive rigid points arranged in a beam-like shape, whose coordinates are directly assigned in the mechanical object component based on those data received from the sensor. The collision model consists in a series of rods connecting two consecutive nodes with a diameter representing the maximum encumbrance of the catheters used during the procedure of the mitral clip. Regarding the vessel model, a finite element approach is used, and two main requirements are taken into account. So the need for a limited number of elements and the handling of boundary conditions. So an external deformable solid has been chosen that represents the effect of both the containing action of the abdominal tissue and the mechanical deformation of the vein itself. Also, an ad hoc meshing strategy has been built up from the 3D anatomy of the patient vessel is obtained by segmenting the preparative CT, and an hexahedral bounding box of the geometry is created. The faces of the bounding box and the vessel walls are discretized into triangular shell elements with different characteristic length. So the volume comprised between the faces of the bounding box and the vessel wall is meshed into tetrahedral elements. The constitutive model is specified with a tetrahedral rotational FEM force field, and accordingly with the ranges found in the literature in order to account for both the surrounding tissue and the vessel wall response. The nodes of the edges of the proximal and distal bases of the bounding box are constrained through the use of the fixed constraint component. The collision mesh is a triangular shell element of the inner wall of the vein and is mapped to the mechanical one. The contact modeling is based on the Lagrange multiplier, so the free motion animation loop and the generic constraint solver are implemented in the SOFA scene, and the time integration is implicit, and on this, which is a first benchmark of the simulation, are conducted some tested to access the stability, the mesh sensitivity analysis, and the accuracy of the real-time algorithm implemented in SOFA. Starting from the same patient-specific model, an experimental setup is realized to validate the simulation. The setup consists of a silicon phantom of the vein mounted on a 3D printing support. On this support, 4 different landmarks are considered for the subsequent calibration procedure to register the simulated virtual model to the physical one. So after defining the simulation setup, we address the problem of data integration to complete the framework and to obtain an augmented reality interface. Our input are the sensor data, and the output is the real-time update of the deformed configuration of the vessel on HoloLens. The entire communication is guaranteed by the ROS publisher-subscriber protocol, and the new configuration of the vessel at each frame is published on a ROS topic at the end of every step, while on the holographic application side, a ROS subscriber node listens to the same topic and update the hologram mesh with the coordinate published by SOFA. For this step, the Unity Robotics Hub is used to set up the communication between the simulation and the holographic application developed in Unity. As we were saying before, the first step to receive, is to receive data from the sensor in the same coordinate system of the simulation. And to do so, we execute a calibration procedure in which the user was asked to point at 4 ad hoc designed fiducial points on the physical phantom with a sensorized probe. The core idea of the calibration procedure is to compute the registration matrix that superimposes the sensor data received in its coordinate system with the simulated model and to receive the transform position at each frame in a continuous manner from the EM sensor. I start the video, okay. So as you can see from the video, we are able to integrate in a coherent way the data from the sensor and then move the catheter interacting with the vessel. I start here the video, okay. And in the same moment to visualize the vessel deform configuration in an holographic model. It is showing the deformation in real time and the streaming in an holographic rendering. Okay. As the catheter advances inside the vessel, the computational cost increases with the number of contacts, as can be seen from the graph, consequently decreasing the frame per second in output of the simulation. However, the final visualization displayed in the holographic device is not worsened by the data stream. It can therefore be concluded that the communication protocol is efficient, while further development are necessary as regards simulation. To quantify the fidelity of the computational model in reproducing the vessel deformation due to the catheter integrating real sensor data, a preliminary validation has been proposed. Even if in the final scenario the input data to the catheter model will be position derived from the FBG sensor, a simplified test was conducted using the EM system only. In particular, a pen-like probe was employed to induce the formation of the inner wall of the phantom, albeit only in a proximal area. Although this test was very simplified compared to the final scenario, it allowed us to evaluate the integration of the developed components and to preliminarily identify the goodness and the feasibility of the proposed solution concerning the simulation, data transfer protocol, and holographic rendering. As you can see in the picture on the right, a grid of markers was drawn on the external software of the silicon phantom, whose position in time was acquired through an high-speed camera and elaborated with a computer vision algorithm to extract the respective markers displacement, which were compared with the displacement calculated by the computational model in the same region, obtaining a very good results. For sure, the simulation in its current state can be optimized both on the software and the hardware point of view. For the software, we want to implement some multi-threadings, maybe with the plugin already available in SOFA, and we want to try an implementation on CPU. Further effort will be spent for sure also on the experimental setup, when also the sensorized equipment will be completely developed. Thank you for the attention, and don't hesitate for a question or advices.
Thanks a lot, Veronica, for the question. Is there any question in the audience, whether it's online audience or the, again, 10 people in the room here? Do not hesitate to either raise the hand and unmute yourself if you're like having a question right now. You can directly ask it to Veronica. And same for people in the room. There is no mic anymore, but you can just come nearby here. You mentioned FBGS, right? As a company with which you're collaborating. Is that the case? Are you collaborating with them?
Yes, they are partner of the R3 project.
Okay. Okay, and I know that there is a PhD student that wanted to work on, who is supposed, I think, to work. I'm not super aware of the latest update, but on this kind of recovering shapes based on FPG information. I'm pretty sure she would be interested to get connected.
Yes.
So
Sure.
I would give her your contact because she could not attend like right now. She's having another like constraint, but I'm gonna give her your contact. Jorg, do you have any question? No? Okay, I thought you might have one. And yeah, you addressed that actually. I wrote the question, but you addressed that a bit later on slide number 16. But some kind of validation of the model, yes, especially the blood vessel model. But if I understand correctly, that you validated that on the like 1, 2, 3, 4, 7, like the 20, 21 points are actually the point of measurements. Is that correct? You know the black points that we see in the video? Are the black points in the video?
I have some problem on my connection.
Sorry. Can you
repeat
see?
your question?
Yeah. Can you hear us right now or?
Hugo, sorry. I
Yeah.
have some.
Okay. So what we'll do? I'm gonna open the breakout. I'm gonna open the breakout session, and I'm gonna join you in the breakout session to ask further questions. Okay. I'm gonna write it.
I can hear you very well.
And if anyone else has an audio problem like Veronica, do not hesitate to write it in the chat. But I will open the breakout session. Okay, so I'm just gonna share the very last slides over there. So I'm going to open the breakout sessions so that maybe Veronica will have the connection fixed so far, and you're going to find her in the room number 3. In room number 2, you're going to have Lydia, and room number 1, you're going to have Mario. Guys, if you want to have, go for a specific discussion, do not hesitate to connect also on your own laptop. I'm going to trigger that in a second. We're going to have a 20-minute break. And that will be like the 5 last minutes to vote for the contribution, award contribution that has been made. sofaframework.org/SW22/vote, and then I'll give you the result of the votings right after the break. Okay, so I'm gonna open the breakout sessions. There we are. Okay. And okay. Reset. Right. And there we go. Okay. I'm going to assign just the speakers. Mario in room number 1. There will be then Lydia in room number 2. And there will be Veronica in room number 3. She's already there. Perfect. So see you in 20 minutes for the closing of the symposium, and do not hesitate to join all the speakers directly in the breakout rooms. See you there. So we'll restart slowly. There should be everyone coming back in 5 seconds here in the main room. Welcome back, everyone. I hope it did not interrupt any last sentence or discussions. Please do not hesitate to use the chat for exchanging emails, contact, and so on before the end of the day of the symposium. To close this symposium, there will be this contribution award selection. Just as a reminder, that were the 6 contributions. Memento memory, sofa cutting, the solver and GPU, JSON reader, tiering plugin, and the 4-wheel Summit XL Twin. There will be 2 prizes, one which has already been elected by the jury a few days ago. I would like to thank again Paul, who is in the room, Camille, Damien, and Eleonora, who are all 3 online. So thanks a lot for taking the time to evaluate all the contributions. That's really cool. I really like that kind of moment just to evaluate and promote the contributions, open source contributions. And these are actually the 2 awards candidates that were actually selected. The first one was, actually, Paul, you were actually selected on both ends, both on public, so the public of today, the symposium public, and the juries selected you as the first prize, the jury's prize, and they were almost almost equality. So that's why I asked for further voting and so on. Between the GPU linear solver and the cutting plugin from you, Vlad. So it was like a few, actually a 2% difference in the votes. Thanks a lot first for contributing. Thanks a lot for all the contributions, both from Paul, Stefan, and the 4 others. So congratulations to Paul and Stefan. Just the last digit for the week. We are still about 65, maybe even more in the main room. There have been today almost continuously more than 80 people joining the event, so that's really cool to see international contributions and presentation from you all. Thanks a lot. That was actually super cool. 30 countries represented, 6 award candidates, which is actually 2 more than compared to last year. I really hope that next year we get even more award competition, so award candidates. So there were a lot of code again this year, plugins, features, bug fixes, but never hesitate just even to apply with a documentation, tutorial, videos, whatever. I mean, all the contributions are most than welcome, and I guess the more there is, maybe the more prizes we would actually do in the future as well. For the rest of the week, I'm going to talk about the technical committee starting tomorrow, but first for next year, a bit later. Next year, 2023 edition, we are actually thinking about making that finally back on site for those who are missing beers and restaurant and also live discussions with the audience. So that should happen next year back in Paris, so that wherever you are, you could actually join the event easily. We will anyway ensure an online access so that anywhere you are on the globe, you can access the event. And if you have any suggestions for next year edition, please do not hesitate to contact me and let me know about any ideas you would have. Tomorrow, it's going to be the start of the technical committee, the 14th already, and we are going to discuss about the recent developments and the future developments to design the roadmap. There have been actually several hot topics in the last weeks, in the last months, and it's going to start tomorrow at 9. For us, it will be in the same room here, and there is another link for people online. The link has also been sent. If you are missing the link, please contact me per email. I would be happy to send you the link as well. We're going to discuss about first, obviously, the roadmap of the 2012 release of SOFA, including matrix assembly, DeepPhysX that has been presented by Robin already today, BIM models, but there is also the cutting topics, which is actually pretty well ongoing currently, the integration on SOFA within rendering engine like Unity 3D and Chai 3D. That has been mentioned as development topics led by different people in the community, and reinforcement learning. And it's just 4 of them. There is obviously more topics to be discussed tomorrow. But stay tuned. See you tomorrow. Tomorrow, either online for most of you, and we'll be in the same room for the dozen of people here. Tomorrow, 9 a.m. CET, so same time, almost same place. And thanks a lot for attending the event. See you next year, and thanks a lot to congratulations, as Eleonora said, to the award winners, to the contributors, and to all the speakers who are actually making the event always cool and nice to hear. So thanks, and see you tomorrow. Bye bye.